enough confidence in the things that I know. I have enough wisdom to see the logic will be shown. I got one chance to show you what I got. I got one chance to show I'm confident or not. Self-evident reason, deductions and conclusions, and the fools are running away. It's not what you say, it's only what you can prove. You better watch your step, you better mind your P's and Q's. You got one chance, show me what you got. You got one chance to show you confident or not. Don't get caught in the matrix of all of these fakers. Society's spinning, and I'm just here living on the ground. Self-evident reason, deductions and conclusions, logically thinking, and the fools are running away. You're flipping over backwards to show me where you think you are. Your model dictates that you never see too far. Shrinking in the distance, you can do fuck all with an angle, and the fools are running away.
Blue marble can't science.
Yeah. Everybody, I don't know why, poor Blue. They must sense a weakness in him. You know, so everybody's going after Blue. We better leave him alone.
He does say the stupidest things. So.
Well, yeah, I know. Yeah, but it's
he doesn't
like
shout as much as the others either.
Picking on him, right? Isn't it? Just because he's
an engineer.
Yeah, and like wrong. But I mean, sloping water. He does say some really stupid shit, I must admit.
Come on.
When you profess that you're right to such a degree that everybody else is wrong, and you contradict yourself regularly, that kind of opens you up for like as a target.
Yeah. Who's his advisor, Larry? Who do you reckon that is? You've not been telling him about the sloping water. That wasn't you, was it, Larry? Must have been embarrassing. I hope you didn't tell him about that.
Well, he did say that the canal, the water in the canal at Ligo, slopes on either end by a foot. So I mean, he did say that, right? And he's willing to bet 10,000 on it. So.
Yeah.
Got another one there, have we? Another one of the land sloper.
Water sloper.
Water sloper, double on either end spot.
We led the new charge now, right? Because obviously the curvature's a little bit tricky. They've done that. So the drop, the hump, and now the slope. And I suppose it works with both variants. You can have a drop slope and like a pointy, like a, I don't know, like a pyramid-y sort of thing.
Yeah.
Yeah,
Yeah,
there's
pick and
the
choose.
drop. There's the drop that's curved. There's the slope that's curved, and then there's the horizontal plane that's curved.
Yeah. And I'm taking it, most of that stuff's come from you and Jesse, Larry, right? You were the guys. You, Jesse, and the guy from Maine. What's he called? What's his name? Jeff.
Yeah, don't forget I agree with the Ordinance Survey UK. So
I agree with the Ordinance Survey UK with the maps.
Well, good, because they said right off that they adhere to the curvature of the Earth when they make their projections. So I guess we're good. They say they apply the curvature.
So they say that there's the drop over distance, and then they see it through optics and say the drop's over distance, but they'll just account for nothing because they know the level's level.
On the maps.
Exactly when they say level and horizontal are different in the context of geography of the planet. They say that. And so we agree with you.
It's okay them saying it, Larry, but I mean, having no proof of it means it's just baseless words, isn't it? Mean nothing.
Well, okay, but when I go out and measure it, somehow that's not proof. I don't know.
Sorry, Larry, you've measured what?
The shape and diameter of the fucking planet with proper instruments over 10, 20 miles.
Larry, we're just on about the water level. Right,
okay,
just the level.
And I'm talking about measuring the fact that all vertical lines are radial to the planet, as easily measured. Yeah, just like the Ordnance Survey UK.
They're all perpendicular to the plane of the horizon, aren't they?
And you keep saying that, which just shows your lack of comprehension.
Well, that's how they are defined, isn't it? Aren't verticals always perpendicular to horizontal?
Yeah.
Okay, now aren't all horizontals parallel to the plane of the horizon?
No. You see, that's your inconsistency. It is perpendicular to the vertical at a point. And if you move down range a mile...
Point.
Yeah, and they're all radial because vertical lines are not parallel. Yeah, just like the Ordnance Survey UK says.
All perpendiculars to a
Have you ever
plane.
eyed anything into the horizon?
All perpendiculars to a plane are parallel, though, aren't they? Larry.
Right? I think he said only good for a mile.
All perpendiculars are parallel to the plane. All perpendiculars are parallel to each other. All perpendiculars to a plane are parallel to each other.
Except that's not supported by measurement. So fuck off.
What?
Have you measured any curvature from left to right before?
It's not measurement. Where's the measurement in geometry, Larry? You use the geometry to form what you're doing, and then you use the measurements to apply the geometry to work out other things. Or to map that stuff. I don't want to argue, Larry. I like you having coming. I like you coming round. I always like to have conversations with people.
Larry, may I ask you a question?
Sure.
I was wondering if you agree with Blue, because we had a discussion and we're talking about LIGO, and somehow we ended up in the canal. And Blue seems to think that the canal, the water, 2.5 miles, he says that following the curvature of the Earth, it drops a foot by either end. Do you agree with that? You want to make a comment on that? What do you think? Because you're a surveyor and all. What do you think?
That's in reference to the LIGO vacuum tubes. And
no. The water, not the tubes, the canal next to it.
The canal next to it, yeah. The canal
Correct,
next,
yeah.
which is a constant elevation, and the LIGO tube is a straight line tangent in the middle, and the elevation of the LIGO tube is not constant because it's horizontal in the middle, and the elevation at either end is higher than the middle, and the elevation in the canal is constant. So we have the LIGO vacuum tube, which is straight because there's a laser in the middle of it. Yeah, it's straight and not a constant elevation. Yeah. And
Understood. But the water, I'm asking you specifically about the canal.
Yeah, okay. The water is the 3,960 mile radius of the planet. Yeah.
So you would agree with Blue then that there's a dip of about a foot, what he says on either end, correct?
From the tangent in the middle, but the elevation is constant. The water elevation is constant, and the horizontal tube is a higher elevation at either end after the 1.5 miles. Yeah.
Yeah, but you keep going back to the tube. Forget.
Okay, then any body of water at rest is a constant elevation, which is a 3,960 mile radius arc, just like the Ordinance Survey UK says in the graphic I put up, which quotes them, which you can quote specifically, and then tell me you agree with the Ordinance Survey UK.
But I think we have we're not communicating here.
Yeah, elevation isn't a circle.
But I'm asking you specifically for the canal, the water. Blue claims because of the curvature of the Earth, there's a hump in the middle, and in either end, there's a drop by 1 foot. I'm just asking you, do you agree or not? That's all. I'm not booking you here. I'm just asking you a question.
Okay. Yeah, that drop is from the horizontal tangent in the middle. And the elevation of the water remained constant.
So there's a drop on either end, but the elevation remains constant. This is your claim.
No, you got to use the complete quote. It's a drop of a foot or more from tangent at the middle. It's a constant elevation, and the horizontal tangent in the middle is going tangent to the Earth.
What's it
And
tangent
the difference from the horizontal tangent to a constant elevation after 1.5 miles is a foot, but the water is a constant elevation, and a horizontal line is not a constant elevation.
Right, okay, Larry, I've just had Stark Odder, because we've been doing this drop thing. Have you seen the RUHIF numbers? But if you just check in the live chat there, we've got 16 100-meter water levels going off in the distance, and they're the numbers there. Now, they've been checked by multiple people now. Stark Odder, he's the latest one, right? They are the numbers for the drop from one end of the water level, not the middle. So why do you put the some sort of a tangent in the middle? Why do you not start at one end like everybody else seems to do?
Because in Blue's comment that you asked me to comment on, it was in reference to the vacuum tube, which is tangent at the middle to the surface of the Earth. So
you mean like Lake Pontchartrain? I'm just trying to keep everybody up to grips, right?
Okay. You moved from a comment that Blue made, which was about the LIGO's tube. Now you want to talk about Pontchartrain.
No. I'm just trying to get the drop from the start point, or versus the hump with the tangent point that you imagine in the middle, right? That's different, isn't it? Because You have to go from one end. You have to go upwards towards where you've got the tangent point.
No,
It's
not
a hump.
upwards. Not in elevation. No, elevation of the Pontchartrain Causeway is constant, and the elevation and the Lake Pontchartrain Bridge is a constant height above Lake Pontchartrain, and Lake Pontchartrain is a body of water nearly at rest, 3,960-mile radius. Yeah, we got that. No hump in the middle. What's wrong with you?
Yeah, there is. Jesse says it. There's a hump. Loads of people say there's a hump. McToon says the hump.
And he gives the number. Tell him the number, Bev.
Yeah, there's a 28.5 meter hump from the Sagitta, right? If you say Sagitta,
Yeah. Okay. Yeah.
That's
yeah.
a hump.
The cord from either end of the bridge is a cord.
it's not a
Yeah.
chord.
Which is, yeah, and then the height.
It's not a chord, Larry.
Oh no! Oh, you see, that's where you're mistaken because it is. Yeah, the cord from either end of the bridge to the deck of the bridge in the middle. Yeah, it does have that 28 meter or 28 whatever you said. Saga to the cord to the arc.
So
Yeah.
you're saying the chord is the shortest straight line distance from one end of the bridge to the other?
Yeah. Uh-huh.
Yeah, but if you were stood on one end of the bridge, then you're expecting to see a drop, aren't you?
A drop from horizontal at one end.
Well,
Yeah.
Yeah,
Because the
point
bridge-
A.
because the bridge is a constant elevation, and if I'm at one end and I set up my auto level, my crosshairs will be looking into the sky, and the bridge will be going below those crosshairs because the bridge is at a constant elevation.
How far
and
will you be looking with this instrument, though? Like just your 100 meters maximum or more?
The 100 meters or so is a specification for where the curve and the drop and the horizontal are so similar that it's not of much consequence. But if you set up your
I thought
level,
it was just to read it accurate. That's what I've always worked on when I'm using them.
yeah,
cycle.
that's why to maintain the accuracy, you pick after 100 meters, you pick up your instrument and move ahead so that the curvature does not accumulate and make
Definitely
problems.
wouldn't look at it, for over a distance of more than 100 meters. Otherwise, it's going to be inaccurate. Yeah.
Well, you'll have to take other considerations if you're confronted with a longer measurement. But by the basic procedure is, you keep moving your instrument along so that your local horizontal tangent and curvature are so close to the same. It's a small, almost no consequence. Yeah, but if you're going for the very high, or if you're confronted with very long distances, then you use angle measurement, theodolites, and the shape and dimension of the planet then becomes very, very critical to your measurement to maintain accuracy. Yeah,
Surely
God.
if you just stayed the same distance off the water, all the way across the bridge, you'd be, that'd be a level line from point A to point B, yeah?
I don't know.
If you measured that, if you were building a bridge and you wanted to level with the water and you measure down from the bridge each time you do a section, then, you'd be level with the water, wouldn't you?
Yeah, just like the Pontchartrain Bridge.
So why is it you see this, huge optical, anomaly, like a big bulge in the middle of it?
That's only because if you are looking from end to end and you have taken your theodolite and lined up on the far end, then you're looking along a chord of the arc of the Earth. Why is that so hard for you?
Because when I see the picture of the bridge that some people have put up, I've seen pictures of that bridge from side on and there's no curvature whatsoever. It's just a level bridge, level with the water.
Yeah, check out. I've just done it was a bit confusing, Larry. I'd never even heard a horizontal tangent. A low, whatever. It just turns out it's a line on a graph on the horizontal axis on the graph. I mean, that's what I'd have thought it was really, but I mean, it doesn't seem to mention the Earth. I mean, you don't think that like blue line on that thing there, you don't think that's the Earth, do you? I mean, are you getting confused, Larry, with the mathematics
you're right.
and stuff?
Yeah, that graph you put up is not the shape of the Earth. Yeah. Okay. So what?
That's a horizontal tangent, though. That's what a horizontal tangent is.
You put up a meaningless graph, so I don't know how to respond to a graph which is completely out of context of the shape of the Earth.
How do you make it a tangent when you say horizontal? I say horizontal plane, and I say that all of those horizontal planes are parallel to the plane of the horizon. But you don't think that, do you? So, how big is a horizontal plane that when you imagine it? Like, because even that's a line on a graph. It's a horizontal line. It's a tangent is a line, isn't it? What are the dimensions of your horizontal tangent planes? I take it.
I refer to the graphic the Ordnance Survey UK has provided to explain it to you. Bring it up with them, because I agree with it with my measurements and my.
So you don't have any of your own stuff. You just refer to a British.
No, you broke me mid-sentence, because I agree with my kit and my observations and my measurement and my 35 years experience. Yeah, I find no disparity with the graph that they presented. And if I ignore any of the components of that graph, then I get wrong answers. And you know what? Follow the money. I don't get paid to produce wrong answers. I get laughed out of the existence, and that's why I'm a chartered surveyor licensed in states for the practice of land surveying in public works.
Can I ask you a question then, Larry? If you've done surveying and that, what's the furthest that you'll ever survey? You know what I mean? Like with your instrument, where would it, optical?
147,000 feet.
What, in one? You're looking across?
Yes, from ridge to ridge across the valley. Yeah.
And what tool was that? Sorry.
I didn't hear that question.
Sorry. Yeah. I just wondered what you used for that. Yeah. What tool was it? Okay.
Stand by.
What was the job? What was the purpose of you doing that?
Did he say 137,000 feet observation?
I think so. 147.
Oh, my bad.
Then I heard it right. Okay.
I think so.
Yeah, like Bev said, I just wonder what why you would do that. I mean, like, is it like you're planning a route for a canal or something, or
zip line?
Well,
that's quite handy because everything slopes away.
Yeah, zip line.
Zip lines are perfect for when you're looking through these instruments because it always drops away.
It's quite a long zip line, that though, isn't it? 147,000 feet.
Yeah, so
divide it by 5,600 a mile, is it? Ish.
5,000 feet to a mile. Yeah.
Mm-hmm.
It's 28 miles.
Nice.
That's a hell of a measurement.
It's a good one, that.
But what for? That's the question, isn't it? I mean, was it just an observation where you just went out to see how far you can see with the instrument that isn't designed to look that far?
But it's not what for, because the moment he left was when you asked him what instrument did you use or what device.
No, he's here.
He hasn't left yet. He's putting pictures up, I think. That's good. Right.
Well,
he's showing us his equipment.
I've seen that tower a few times.
That looks like a fancy station there.
Okay.
Yeah, he's at a high elevation there.
Wow.
Right. So what
Yeah,
was the job?
I was measuring the elevation of the radio tower at 27.69 miles away. And the only way that makes sense is with 511 feet of curvature and 80 feet of refraction. And I duplicated that measurement from only 1 mile away. And in both cases, I get less than 2 feet of difference in the elevation of that tower.
But we do already know how tall the tower is, right?
No.
You
I measured
didn't
it-
know how the elevation of the tower.
You see, you don't listen very well. I said I measured it from 1 mile away and the 27.7 miles away. And after applying the 511 feet of curvature and the 80 feet of refraction from 27 miles away, I get less than 2 feet of difference when I was only 1 mile away.
I don't look, Larry. I don't want to seem as though I'm attacking you or anything, but we did ask you what the job was. So
to determine the elevation of that light on that tower.
Did they not already know what the elevation was of the light on the tower? The people that employed you to work this out, right, as a job.
It was not a paid contract.
Okay, right. So we start again then.
All right, okay, yeah.
Can we start again, right? What is the furthest you've ever been employed to do this? You know, like using your actual surveying techniques, not newfangled ones that you've just made up that you do in your spare
those
time.
are not newfangled ones. Okay, the longest I've ever been dealing with is in 8 and 10 mile observations while surveying up and down the Santa Ana River in Orange and San Bernardino County, California, where we made major maps for dam construction and flood control. And yeah, it went for 50 fucking miles in 5 and 8 mile lengths.
What, and did you ever add anything? Say if the river's running, did you add anything onto that river running? You know, like how would you actually, you know, like, because we've been talking about the water level here for a while, and some people tell us that one end of the water level will be lower than the other part of the water level, which would actually mean that it would be running and not actually, you know, level. So, like, when you're surveying a river, what were you surveying the river for? I mean, to see how much run is on the river.
No, because we know how much run is on the river by its elevation grade as it goes as it flows to the ocean, and we were making a large area control network for topographic mapping and engineering and land takes for flood control infrastructure.
Yeah, did you so your observations though, when you were, you know, doing like when the actual surveying to try and get the actual, you know, measurements, you did that using the normal techniques, you know, within 100 meters or, you know, whatever you're doing to get the...
No. I said 5 and 8 mile section lengths, not 100 meter.
What, so if you're looking like down the river and you'll see the drop of the earth, you think, as well, is that what you're saying, in 6 miles?
Well, and the measurements also return that drop, that radius of the earth, yeah.
Well, so the river's dropping with the earth as well, sort of thing? Like, because if you're at the other end, looking back to where you are, you know, when you're seeing the drop, surely it's dropping the other way. Then what happens with the river then? Surely it goes up the other way.
Yeah, you can play that silly argument because,
no, it's not silly. It's a logical...
It's a constant... Yeah, elevation is based against the radius of the earth. So even if you have thousands of feet of, quote, drop from a local tangent, that does not mean it's thousands of feet lower in elevation.
We're in the UK here, Larry, and elevation here is above mean sea level.
Yeah, I know. Just like it is here.
So it's not reference to the centre of the earth then, it's reference to the mean sea level. Average mean sea level, sorry.
And mean sea level has a radius relative to the center of the earth. Yeah, I'm glad we agree with that, just like Ordinance Survey said.
Sorry, you say what? All mean sea levels are referenced to one central point. Is that really? I don't think that's right. I think they're all referenced to their own mean sea levels, aren't they? The elevations.
Yeah, and mean sea level in England and mean sea level on the east coast of the United States are the same because of the radius of the Earth that defines the ocean between us.
At the same elevation, you think?
Yeah, the same elevation, zero mean sea level. Yeah.
Okay.
0 is level, definitely. Yeah,
Yeah,
I'll
yeah.
go with that.
I get it. So when they all get their own mean sea level, right? They're all say, because they can't all be the same, right? No, they're not all 0 to 0, are they? The mean sea levels, that they are different, aren't they, for different areas? There's no way to actually reference them to each other because they're all their own mean sea levels. I mean, you must have heard the problems they had in the UK when they first started trying to work out the mean sea levels. Yeah,
and those differences are relatively small. They're only in the couple of feet range.
What do you mean? They're relatively... Like, having a difference of mean sea levels of a couple of feet is a bit of a problem, Larry.
Yeah, that's why they addressed it. But the couple of feet...
They didn't. They just went to 1.
Yeah, because of the distributions of gravity and tide and all that.
No. Just because of the discrepancies between the other ones. It was just easier to take it from 1, which is what they do now, right?
Okay, take that singular point that UK uses,
Newlyn.
and from that point, measure the elevation against mean sea level of New York relative to that single point in UK.
They're on their own reference, Larry.
I know, but I said compare the two references, and you'll find it's only a couple feet different because of the
How
irregular.
do you compare them?
By measurement.
How?
But because of 3,000 miles of ocean, yeah, that does get pretty fucking hard. But we have the shape of the Earth as measured, so yeah, that's not hard when we measure the radius of the Earth first.
But that one I'm interested in, by the way.
You've got to measure the radius of the Earth. That's not hard. That's been done hundreds
How
of
do
years.
you do that?
Yeah, I'm not too sure about that one, Larry.
I do it in ways that you don't believe,
Go on,
so there's no point
tell
in
us one.
discussion.
Tell us your best one.
Yeah, I've been using these tools for, 25 years, and I've never accounted for any of that. So you go ahead, mate.
Have you ever measured more than a few hundred feet in any direction? Did you do 10-mile observations?
No.
Yeah,
Okay,
you have. He has observed things at 10 miles. Spot on.
Oh, sorry. Yeah. No. I thought you meant using the tools.
Well, you have. You've looked through your auto level and seen 10 miles things 10 miles in the distance, right?
Yeah, but not at work.
Well, yeah, you're not actually doing anything, but I mean, the observation has been made.
Oh, I've done it. Yeah. There's definitely some sort of optical drop there. Yeah. Or whatever you call it. It's below the crosshair of the horizontal.
I'm sorry again, Larry. You said measuring the radius of the Earth. Now, how do you do that? Can you tell me? I'm a very fucking outsider in this kind of question, and I would like to know. I'm very curious.
By measuring the angle to stars from vertical at distances significantly separated, like 250 and 500 miles.
That sounds fantastic.
You mean a sextant? Using a sextant or what?
No, the theodolite I showed you. I put my instrument on the screen.
You use a what for measuring?
Theodolite.
Theodolite.
A wild T2, is it, Larry? Model.
T2, correct, and T3 on occasion. Depends on what I'm doing.
Pretty old school.
Very old school. Because old school still works.
Yeah, I love the old school
Definitely
stuff.
right angle triangles. Yeah. horizontals. Yeah. Triangulation.
Theodolite for angle.
Okay, that's the instrument I use when observing the sun. Yes. And it measures to a microradian. Yes. Not looks like, not a sextant, not a rule of thumb.
Why are you looking at the sun with that for, by the way?
To measure the radius of the Earth. You got to keep up.
Sorry, no, I'm literally just, I'm in construction, and I'm just asking questions because there's questions I've got. I've not done observations like you have before.
Okay. Let me roll that back a little. I apologize. Yes.
Thank you. Yeah,
construction grade equipment is not as high an instrument as that. Normally, correct. That is a very high level instrument, and in construction you use a lower grade of instrument because it satisfies the requirement.
Mm-hmm. So there's no like are they rectilinear, those lenses and what have you? They're like, there's going to be no, like you're going to see. I don't know what the word is. You know what I mean? Is there going to be curvature added by the lens or anything like that?
It's the highest grade of optical tooling, and that's why instruments have a crosshair, so you're measuring through a specific point through the optical path. And as you move the instrument, the crosshairs, you're measuring the angle from where the crosshair was on the target, an angle to where the crosshair is on the target. So the lens has nothing to do any curvature or radial distortion of the lens, which at that focal length and for that tiny field of view is very, very, very small. But we're not measuring across the field of view. We're only measuring at the incident of the crosshair.
Did you get that, guys? Did you get what you want?
Yeah, sorry, yeah. No, I'm doing something at the same time, so I'm just sorry. Yeah, but thanks for that, mate. Yeah, I've just So how far do they say that these things are capable? Are you saying that you can look 10 miles with this thing and it be?
It's looking at the sun.
That's 93 million miles away, isn't it? So they say.
Yeah.
Wait, sorry, he's looking at the sun
to get the radius of the Earth with a really old.
Looks like something from the in the military or something.
Yeah, I've seen that. Have you got some scratches on the lens there, Larry?
No.
What, somebody been turning the cap with a stone in it or something, and
no. Where do you see scratches?
It's got like circular marks on it.
Oh, the circular marks? I mean, the precision reticule that is the same diameter as the sun? Yeah.
What, the same diameter as the sun?
Same diameter as the sun.
Circular reticule, the circle in the reticule is 32 arc minutes in diameter, as is the sun, and that is used to align.
What focus have you got? What magnification have you got on that scope?
24x, and it's only got a 1 degree field of view.
A 24 times scope, and you're getting the sun. That big.
And or Polaris, or a strobe light on a radio tower 25 miles away. Yeah, I can do that. Isn't that amazing?
24 times scope's not that good, though, really, Larry.
Couldn't you get that more like in the middle? That last bit?
Yes, I could. But when I was holding the camera, yeah, I couldn't do both.
Oh no, that's fair enough. No, I just didn't know if there was a reason. That was all. No, okay, that was a bit awkward, like.
Yeah.
I'm sorry, I really don't get this. Shouldn't the crosshairs be in the very middle of the frame?
Yeah.
But is it?
Yeah, the crosshairs at the very center is for measuring angles across precision targets, and the sun is so fucking big that, yeah, it's hard to, you can't pick out the center precisely, so you use the circular reticule and get concentric with the sun, and that's,
Larry,
and that's the same.
I think
That's the same.
he means shouldn't the crosshairs be in the middle of the picture? I'm asking a similar question.
The picture or the frame?
Yeah.
We just talked about that. I was holding a camera, and I was taking a picture. I could not do both because the sun moves so fast.
But then, sorry, then that's not the sun. That's not the whole sun. That's something else then.
No, that's the whole sun.
It cannot be.
It just happened to be in the bottom half of the picture. Like, where's the top half of the other
But sorry,
stadia
if we are seeing half of the picture, then we should see only a part of the sun also, because it's supposedly in the middle of the picture, going around the middle of the picture, right?
It's because its angle of the camera is taking the picture on a weird angle, isn't it?
No, I'd lined up on the sun, and I pulled up my camera, and the sun had moved some, but I was just taking... Yeah, so I was taking the picture, and yeah, the crosshairs were no longer lined up on the sun, but it didn't matter because I was just taking a picture. This is not a measurement. This is just a picture of what I see.
But why is it black all around it, then?
What?
I don't get this picture at all. Why is it black all around it?
Because it's got a solar filter on it, right, Larry?
Right.
Obviously, because he's looking at the sun with a surveying instrument.
24
yeah.
times.
But it's not in the middle. The crosshair is not in the middle, but the sun is in the middle, supposedly.
No,
No, that's way off. Like I say, you can't even see the top stadia hair.
I could.
Yeah,
move.
so where is the rest of the moon? The rest of the sun?
The sun is there.
Yeah, the sun's there.
That's it.
I could have driven the scope and lined up on it, but then by the time I take the picture and fiddling around, but I didn't care because
you can't have only ever took one picture and not got it right, Larry. Have you never took one to get it right?
No, you're right.
I never did better pictures.
No, because taking that picture serves no purpose other than to say, "Oh, look, a pretty picture."
You're just looking at the sun, though, Larry.
Yeah. So what? I didn't take a picture.
Sorry.
I didn't take a picture when it was completely perfectly lined up because I was busy doing other things, and I don't need the picture. Doesn't do anything. It's just a document of what it looks like through the scope.
Yeah, that's all right, Larry, man.
So when you do the surveying, if the pictures don't mean anything, then what do you people just have to take you on your word that you made a measurement, and that proves what? Like, because I'm struggling. Apart from the fact that you're looking at the sun with a surveying instrument, I mean, I can understand that it moves in the sky. I mean, yeah, but how does that prove the radius and of the thing that you're standing on? Like, what's the fancy calculations that you do once you've measured the sun? And I take it the angle that you take. Where's that from? Do you take from the horizontal upwards towards the sun, Larry? How do you calibrate your theodolite? How do you how do you know that when you're it is vertical, it's vertical, and when it's horizontal, it's horizontal? How do you know that that's right? Because you get how accurate it is. I bet it's really accurate, right? An arc minute or something like that.
Far better than an arc minute, and I get my horizontal and vertical the same way you do with your auto level.
Right, okay, well, my auto level has to be calibrated, and then I perform a 2-peg test to make sure.
So there you go. You see?
How do you do yours? How do you make sure yours is correct? We do a 2-peg test, Larry. If that's a hint.
Yeah, and periodically with the theodolite, yes, you do make checks and adjustments, and much the same way, except the
What do you mean
theodolite.
adjustments?
What do you mean adjustments? You said calibrated. Yeah, you adjust to get a calibration value near 0. Yeah, that's what you do.
Okay, so you do that with the theodolite, right? You do it.
Yeah.
Okay. I don't with the theodolite with the auto level. We don't calibrate it. We just use the 2-peg test to check it's still in calibration.
Yes, and
Yeah.
if it failed the peg test, you'd pull out your little bitty screwdriver and adjust it, wouldn't you?
Nah, I'd take it back to the calibration guys.
Yeah, and they would take out their little tiny screwdriver and adjust it. But I happen to have the skill to adjust my own equipment. Why is that so weird?
Sweet. It's okay. How do you adjust the calibration?
By making a chain of measurements, much like you do with a peg test, and make sure that when you put the instrument in all the different orientations, it gets very, very consistent down to about a microradian, which is less than 1 arcsecond. Yeah.
No, it's auto level.
Okay, autolevels and theodolites are very different animals.
Yeah,
but
yeah.
they both can be adjusted, and they both have procedures and methods of calibration and adjustment.
Not vertical angles, though. There's no vertical angles on an auto level.
No shit, Sherlock. They're different animals.
I know, that's why I was questioning.
Yeah.
Because you did
So,
say...
yeah, when you're doing your peg test, you're not measuring angles, you're measuring on the staff. And when you're using a theodolite, you are measuring angles. Okay, different animals, different procedures,
Right.
and yes, they have adjustments.
So you measure an angle for your theodolite.
Amazing. Isn't that amazing? The tool is built to measure angles, so to calibrate it, I measure angles. Isn't that weird how that works?
Right, but that wouldn't calibrate it to horizontal, would it? That's what I was asking. How do you calibrate like an angle's an angle? I mean...
Okay, because I calibrate it to vertical, the same as your auto level, which is sensitive to the vertical because it's driven by gravity, much like my theodolite instrument is all aligned to the vertical. Your auto level measures or responds to the plumb, and through mirrors and prisms, it generates 90 degrees to plumb. It is the same driving force in a theodolite, a manual level, and an auto level is the plumb line. Yeah.
No. When you send it away, you get it calibrated, right? To horizontal, the auto level. What I was asking you was, how do you know your theodolite is the same? How do you know when it reads, is it 0 or 90? What does it read for the horizontal? Larry, what's your reading on the side? Is it a 0?
No, 0 is vertical and
Okay.
90 is horizontal.
Horizontal, right, okay. So how do you know when you are horizontal at 90? How do you know that is horizontal?
Through methods of procedure, of operation of the instrument, and recording the numbers and seeing how they coincide when looking through the instrument in one direction. I rotated 180 degrees, look at the same element, while everything is now reversed, and making sure that it comes up to a nice, fine, tight, little precision number, and I can set my level right up next to the instrument, and it's looking 90 degrees to vertical out there at the horizontal, and I can level up my theodolite to be 90 degrees to the vertical, and the crosshairs are on the same target within minuscule variation. Yeah, it's called testing. Yeah, you talked about a peg test. I can do the peg test. And if it fails the peg test, I can make the adjustments. And theodolites have different procedures, and yes, it's all angular driven because it measures angles. That's what it does. And it measures those angles from the same driving gravity force that drives your auto level. Yeah. It's a nice little tight system there. Yeah. It's all self-checking. You can check instruments against instruments, and instruments can be checked by procedure. And adjustments, if required, can be made. And it doesn't take a fucking rocket scientist to make an adjustment when you have an instrument which is essentially self-checking by methodology of its operation. Isn't that amazing?
I didn't really get the procedure that you did. You zipped through it there, Larry. So at some point, I would like to hear it. So I don't.
The procedure has enough nuance and detail and methodology that in a YouTube chat, we're not going to fucking get very far with it because, yeah, you're going to have to study instruments, get other instruments. All you have is an auto level. You have no experience with any other kind of instrument, and you don't measure anything bigger than your fucking backyard. So there, okay.
Right, well, I've got to go back to the calibration center for my auto level. And I was just checking what you would say, because I'll be asking the guys and going and having a look at the bed that they use for calibrating the instruments. So I just wanted to, so I can compare the difference between the two. Thank you very much. But like you say, the theodolite is just an angular measuring system, isn't it? I mean, you wouldn't normally do elevations to first order, would you? Or would you? I don't know.
No, you're right. Absolutely right. Vertical angle measurement over multiple miles would not qualify for first order elevations. You're right. It would be a practical and valuable elevation, and in mountainous terrain, that would be the high, as accurate as you could readily achieve. And no, nobody puts a first order elevation on a mountaintop because it's too fucking expensive and hard to do.
Well, yeah, but anywhere really. What tool would you use for a first order?
A first order level. I wouldn't use a theodolite for first order because that would be incongruous with the specifications.
Would you consider an auto level good enough, or would you want to go higher, more precision?
Well, auto levels come in different grades. And so I would get a first order auto level or a first order manual level, and I would not use a $300 auto level that you get at the Home Depot.
99 quid this one cost.
Oh, there you go. I would not use that for first order levels because it's incapable of meeting the specification. So, yeah, I would use the right tool for the job.
That's really weird you say that, because they said it was the best level that they've got for elevation.
The best level they have,
yeah,
or the best level the best level that exists?
Well, I don't know. Like, what's the difference for you? I mean, I know I've seen coincidence bubble levels, but they go into the thousands of pounds, and you know the only difference is 0.3 of a millimeter over a 1 kilometer double run. I mean, that's how accurate do you usually with your first order measurements?
Oh, well, I meet the first order specifications. So if you look up the first order specifications, that's what I operate with. Yeah.
1 millimeter per 1 kilometer double run. It is the tool that we use. That's what it's graded at.
Yeah, and I don't think you could do that with your instruments.
No, that's the one that it is. Yeah, that's what it
right.
says. It's really good,
right.
really, really good, Larry.
Well,
for the price as well. It's fantastic.
Good. Then get yourself some temperature compensated rods, the proper turning points, and go through the full method and run 10 miles.
What, you need a rod?
You would need a pair of rods that are thermally compensated and do all your procedures.
Did you not tell Bob that? Bob seems to think you can use anything for you don't need measuring rods. Bob the liar guy, the one that said he'd measured the drop of the water level across the lake.
Are we talking about the special sticks? The magic sticks?
Special sticks, yeah.
Oh, my bad. Yeah, okay.
Yeah, I'm sorry. If first order requirements for first order elevation determination 10 miles away takes a lot of procedure and a lot of care. And if you use your instrument, you probably get kind of close, but you would not get first order.
Could you not just do the 1 kilometer double run and just sort of start with a new base once you've done that to check your accuracy once you go back for your loop back? Once you've done that, then surely you've established with the error check you do a few times. Like, could you not just progress that on further?
Yeah, if I needed to establish a first order elevation, and I have, at many miles away, yeah, you run out a mile, and then in the morning, you run back a mile in the afternoon, and you come back the next day, and you do that for weeks on end to establish a very high accuracy elevation relative to the starting point 10 miles away.
Yeah.
You do it in sections. You're only running the 60, 80 meters per measurement, and yeah, you're leapfrogging along, and you're running out and back, and you're doing all kinds of stuff to hold on to that millimeter and the square of the kilometer of the distance run. Oh, yeah, I do all that. And I don't use an instrument as low grade as yours, and the instrument and the rods I use...
did you say the square of the kilometer?
The specification, which I don't have committed to memory.
It's just elevation, is it? You'd go in the vertical change all the way along, right?
Right.
And that's it, isn't it?
Yeah, that's it. Exactly it. You got me.
Okay.
Exactly right. It is a one-dimensional measurement. So I'm measuring the elevation difference from point A to point B. They're separated by in excess of 10 miles, and I do it in little sections, going out in the morning, coming back in the afternoon, and it would take me a couple of weeks.
Yeah, like old school, like in the UK when the Ordinance Survey did their original thing, they did lines, didn't they?
It's not just old school; it's current school.
That's good.
Yeah,
let's call it spirit leveling for measuring elevation, right?
Yep, exactly.
Okay.
Right.
Using Euclidean geometry, right?
Oh no, it's not even that because it's just one dimensional. So yeah, it's just sums.
It's just one dimensional. What do you mean by that?
It's just sums. You're adding. You're taking the rod readings and just doing the arithmetic. It's not
plus or minus.
Right. Exactly. Good. And that's exactly where we agree because with a proper instrument, proper rods, and proper procedure, if you have to get a first order elevation 10 miles away, it'll take a couple of weeks, a lot of effort, and a very high grade kit.
It's already been done in the UK, right?
Oh, in most parts of the civilized world, actually, yes.
Yeah.
But not to mountaintops. But typically not to mountaintops, along where elevations are critical, like railroads and canals.
Yeah. Well, actually, we had Dawn round the other day. What's your opinion of mountaintop to mountaintop observation if you've got 3 mountaintops and you're doing your angular measurements from mountaintops, like a triangulation? Do you have triangles with 180 degrees?
I rarely deal with triangles of that magnitude.
Of what? The magnitude of 180 degrees?
No, a magnitude of the square area of the triangle, which defines that spherical excess.
Sorry?
I rarely get the opportunity to be dealing with triangles that are a couple of hundred square miles each.
Okay. But they'd still have the triangles with 180 degrees, right?
When you get very large triangles, it is no longer 180 degrees, and I don't measure very large triangles, not in the past couple of decades since they invented GPS. That is all kind of...
Do you mean no longer 180? It's a triangle.
Yeah. And on the surface of the Earth, since the instruments were all oriented to vertical, and vertical is radial, then you end up with an excess in the angles measured. Yeah, we do that. Yeah, just like the Ordnance Survey UK says, they've got tables and formulae for all that good shit.
It's
showing you
3 coplanar points, Larry.
Well, okay, the word coplanar is where you run awry. So, yeah, obviously, as per the Ordnance Survey UK, you have to involve the shape of the Earth when you're measuring very large distances. Yeah,
no, triangles don't change because of the size of them. What do they call it? Scalar, is it?
Yeah,
isn't it a function of triangles?
Why don't you? You should brush up on what Ordnance Survey UK says, and then you can get back
to triangles.
Yeah, triangles across the surface of the Earth when you're involving hundreds of square miles in a single triangle. Yes, because the instruments are oriented to vertical at each location, and since vertical is radial to the Earth, and when you get these great separations, you'll find a couple of extra arc seconds per angle. Yeah, because they are not coplanar, they are oriented to vertical, and vertical separated by many miles is significantly different than parallel, which is your assertion that you've never observed or tested or even read up on.
I've not really done that much on, because
Yeah.
I do have a proof, though, Larry, that triangles only have 180 degrees.
When they're small, when they're only a few tens of square miles, yeah, that's within our ability to measure. But when you get hundreds of square miles, like measuring across mountaintops, like in the western states of the United States, where that happened quite often, and when you're measuring chains of triangles across a continent that's 3,000 miles wide, then that shit matters. But when you're measuring something only the size of a municipality, it's not that critical because it's a smaller quantity than instruments return. You have to get the big distances, and with big distances, all these little things add up to become big compensations. But that's when measuring, as you pointed out, across mountaintops, not across block corners.
Yeah, sighted. You're on the top of the mountain with your telescope, and you're looking. You see the other mountain top, and that's your start point. And you do that 3 times, and you get those 3 angles. That's a triangle, right? A coplanar. Three points.
Yeah, I can't see what's so hard to understand about that. Seriously.
I don't know. Why did you say the word coplanar?
Because it's 3 points, Larry. That's a triangle.
Well,
it doesn't matter about the elevation of the actual peaks. It's just line of sight. Bang, bang, bang. 3 lines.
And the instrument is leveled up to vertical at each location, and since vertical is not parallel to each other when separated by great miles, yeah, then the angles are in excess. You have to go big, and when you go big, then these things become very appreciable, because as the Ordnance Survey UK says, the Earth is 3,960 miles in radius, and when doing large area triangulation, you have to account for the fact that we're on a planet.
I can't see how you can have 3 points, each of which 3 guys on 3 peaks, 3 points. It can only be a triangle. 190.
And how far away are they from each other?
It doesn't matter.
No, it does matter. It absolutely matters, because
How
it
far?
matters.
You decide, Larry. Give us a number. Let's say they're 10 miles apart. All of them, because you could easily see 10 miles, can't you? I mean, you've done an observation over 10. Right, so let's just theoretically make one of the mountains, not really a mountain, let's call that 100 feet above sea level. Let's put the other one at 200 feet above sea level, and the third one at 300 feet above sea level, right? And let's just put a guy at each of them, A, B, C. And let's have them look at each other and measure angles from from B to C. You make a triangle. The distance. You want to know the distance between them all? Let's make it an equilateral.
Yeah, exactly. So where's any curvature there? It's just straight lines to the observer. This must be, like a bit tricky for you, I'm sure, trying to figure that one out. It's so easy that I just don't understand why you don't get it. Maybe things have been blurred by all these new bits of equipment you got. Stop looking through stuff and just focus on the logic.
If the mountain peaks are only 10 miles apart, you're still going to get. You're only dealing with like 45 square miles, and at 45 square miles, the spherical excess is not even hardly an arc second. I said you got to go big.
It can't be measured at more than 180 though, Larry, can it?
If you're only 10 miles apart on a side on an equilateral triangle, yeah, you don't have much to worry about. It has to do with the area of the triangle. If you've got an equilateral triangle, 10 miles on a side, you're only dealing with about 45 square miles. Not a lot. Yeah. That's small. Have to go big, man.
Well, so they're straight lines locally. Straight lines locally again, isn't it?
Yeah,
that's what
you've got to go big to break the laws of mathematics, right, Larry?
No, you got to go big to see the effect of those mathematics. Because the Earth is fucking big. Yeah, you got to go big. You can't be measuring like 0.00001% of the Earth and think that it's all going to be so grossly obvious. You got to go big.
Curvature hunter.
Triangles with more than 180 degrees. What's the biggest angled triangle that you've ever done, Larry? Or if you haven't done it, what's the biggest one you've ever heard of somebody doing? I'm curious. I mean, I like maths. See, I was of the understanding that it was an axiom, really, like a triangle axiom, that triangles always have 180 degrees, especially straight lines and stuff.
Yeah, me too.
Got this. I'll just give it a quick read out. Just to refresh.
That's interesting, though, isn't it? That they're using angles to measure mountains, not actual, like using the auto levels or anything like that. They're just using angles.
Well, in the process of mapping, right, to work out elevations and all of that, right, you're not really after the elevation, but what you're after is knowing where the peak of the mountain is for your measurements, for plotting it on the map, right? Yeah. Two-dimensional map. You want to know where the peak of the mountain is. For purposes of laying the contour lines down, you can map that on afterwards at any point. But you need to know where the triangulation of all of the points, right? So knowing where the peaks of the mountains are would be. And also, they're the trig points, right? When they triangulated the UK, all of the high spots are where they actually triangulated it from. Right? Yeah. So that is purposeful, right? Because what you have to do is you then employ those measurements of those triangulations and then the accurate distance, horizontal distance measurements between the two, and then you can put it all on a map, right? No doubt there will be areas that you can put on the map that will give you a measurement distance because you're doing everything to scale. It's the whole purpose of doing a scale map, right? Then you can plot that point there and you don't even really need to measure it. You could just triangulate it from a different position and then work out whether you're right for the distance measurements to it. It's genius, really. I mean, that's why they only laid down lines in the UK. Because once they've laid down those lines, then that can spread out, like a...
But if you're looking at a mountain, you want to be close to it. If you're going to be looking up to it, you're not going to be like 40 miles away, 50 miles away, looking at a mountain, trying to figure out how high it is. You're literally going to be doing it close.
No,
if you're
but
going to be
like I say,
working out angles.
when I go to the local one round here, and it's got all of the different points on it, it's all of the different peaks of the different hills that are around this area, right? And one of them was the Isle of Man, 85 miles away. So
yeah, so how did they
must
actually
have
get that
known.
first order measurement? Yeah.
Yeah.
But
It's got to
then
be
again,
through triangulation, hasn't it? The only way that they can get that sort of a distance. You'd never have done that by boat to the Isle of Man.
But we have to hand it to the Brits for when they measured the elevation of Mount Everest. They did it by everything you just described: triangulation to get its horizontal position, vertical angles by theodolite to get its elevation, applying curvature and refraction. At 95 miles away, they got the elevation of that mountain, and in 1953, they redid it using a wild T2, thank you very much, and they got much closer to the mountain, only 50 miles away, and got the same elevation, give or take about 20 feet. Yeah, curvature.
So they got the elevation correct.
Yeah, they did. They got the same elevation both times. And then just recently, the past couple of years, they went up with more theodolites and GPS and still got the right answer. So right, but only when applying the shape of the planet and vertical angle at many miles, getting the right elevation of the mountain peak, and by horizontal angles and triangulation, getting its correct latitude and longitude.
Would they have they wouldn't have had to add on extra angles when they were viewing that the first time, were they? From 95 miles away. I mean, that sounds like quite a lot.
Yeah, it was quite a lot. But the Brits are the best surveyors in the world.
But that triangle that they'd used when they did that would have had 180 degrees, wouldn't it?
No, the triangles they had were the same triangles you get measured on the planet, and when you're dealing with very long sides, all aspects of the triangle, including the spherical excess, by large area triangles of many hundreds of square miles, yes, they did a full compensation because otherwise they would have been incompetent, and they are not incompetent. They got the right answer, and then coming back with modern technology, get the same answer.
But
give or take.
The triangle had straight lines, didn't it? Must have done.
Yeah. That was before the GPS and all the curvature came in, surely. All these first order measurements that they were making around the 1900s.
It's like trigonometry, as far as I know, always works with, you've got to have 180 degrees in a triangle. The whole principles, if you know the geometry behind a triangle, especially a right angle triangle, which is what we would end up using for calculating your height or whatever. So listen to this. This is quite important, right? It says that if a straight line meet two straight lines, so that's three, right? One straight line and two straight lines, so as to make the two interior angles on the same side of it taken together less than two right angles, these straight lines, being continuously produced, shall at length meet on that side on which the angles are less than two right angles, right? So two right angles is 290 degrees, 180, meaning that they would meet on the side that there are less than two right angles, and the other angle where they meet would be the conclusion of the two right angles, right? So 180 degrees. Now that's our axiom. I call it the triangle axiom because it does state that triangles have 180 degrees. Sort of a mathematical law, I call that, if an axiom. Self-evident truths.
Yeah, and you could replicate that on the Earth if you get very, very large areas, and then you'd have to compensate for the shape of the Earth, and to get those instruments to be coplanar would be a very, very tough task, and yeah, you'd get 180. But since the instruments are oriented to vertical, which is local, and they're separated by great distances, then those angles do not return a total of 180 because it's not the same or triangle you just described. You got to deal with the shape of the Earth, much like the Ordnance Survey UK. I just put that up there. They went through all the formulae for dealing with spherical triangles or triangles measured across the surface of the Earth. And notice how complicated that math is. But you know what? That's because the Ordnance Survey are competent, much like the surveys that were done in Everest in 1860, in 1950, and in the 21st century. Yeah, it all comes together with a nice, complete, homogeneous, repeatable science. What I can't repeat is anything dealing with elevation and ignoring the shape of the Earth when dealing with more than several hundred feet. Yeah, that's what I get. I can't replicate flat. My measurements are chaotic if I ignore the shape of the Earth.
If you do it locally, like I do, then actually, you don't have any of the effects of that, do you?
Well, yeah, you got to go big, and that's when they say.
No. But I mean, isn't going big making it like there could be problems optically? Has that ever crossed your mind?
Yeah.
Right.
Yeah, that's where I have a problem as well. I get that spot on, right? Because it doesn't alter the geometry, surely. It's straight line triangles only have 180 degrees. So I'd say there must be something else going on, Larry, wouldn't you?
No. You take a big triangle and then take the vertices of those triangles, and when you measure the angle for that to be 180 degrees, then the instrument at each corner must be parallel to the instrument at the other vertices. And when you're on the surface of the Earth, you're orienting to vertical. Vertical is a problem because it's not parallel, as is demonstrated by the measurements.
But you are looking over massive distances.
Yeah, that becomes significant when the distances are significant.
Don't get any of these problems when you're doing it on like smaller scale.
Measure up a piece of continent. Measure up the archipelago of UK. Yeah, those are significant distances, and the UK, in their complete competence, do in fact take all aspects of triangulation on the shape of the Earth, elevation of the shape of the Earth, and they make their maps in projection. Yeah,
absolutely.
As Ordnance Survey UK has stated emphatically numerous times.
Well, thanks for having a chat with us anyway.
Yeah. I'm making me tea. I like it. Yeah. Please feel at ease, Larry. This isn't like an interrogation or anything. You came in to join us. We're just trying to get your knowledge and wisdom. But I must say, I am confused. I do understand the geometry of basic geometry, right? And as I know, like I keep saying, the triangle having 180 degrees is sort of a fundamental basic of geometry.
Well, yes, it is. Yes, it is. And when you measure that angle, the vertical axis of an instrument would have to be normal to that plane of the triangle. And since you align it to gravity, the vertical, just like your auto level, then the vertical at those three vertices are.
You do sound like.
Vertical,
oh, sorry.
Then the vertical at those three vertices, being separated by significant distances, are significantly not parallel, and the interior angles have a slight excess on the order of 1 arcsecond per 75 square miles. And that 1 arcsecond is the sum. So that means at each vertex is only 1/3 of an arcsecond. And that's very hard to measure unless you get very large triangles to where the spherical excess is 20 or 30 arcseconds. That's just it. When we're talking spherical excess of the interior of triangles, we're only talking about tens of arcseconds on big triangles. We're not talking about like a half a degree, a tenth of a degree, or even we're talking like small amounts. But when you go thousands of miles, like across the United States or the many
You can't measure thousands of miles, Larry. We know that.
Not
you can't.
right.
But you can't cite it, and if you can't cite it, I'm definitely not interested in it. I was interested in like, what's your error margin at 95 miles? You know, I can imagine whatever you see through the crosshair, right? It must block loads. I mean, how big is the area that your crosshair is covering when you're looking over something like 95 miles?
Well, at those kinds of distances, a single angle could take a week to measure through repetition, working at night with lighted targets on top of towers. Yeah, that would be a major undertaking. And yeah, measuring across
nighttime surveying. That's why you need your pattern lights. Got it.
Oh, now refraction. So you're measuring refraction, not earthquake. Gotcha. Cool.
No, we're measuring. Yeah, you're right, guys. You're right. Your Ordinance Survey UK.
You're looking.
You said you agree with the Ordinance Survey UK, and yet everything you say disagrees with what the Ordinance Survey UK says. So at this point,
I
bid you adieu, because refraction has been studied for 500 years. Geodesy has been studied for over 500 years. The shape of the Earth is not in doubt, not in question. Its dimension has been measured millions and millions of times, and the orbiting of satellites proves the shape and diameter and dimension of the planet over and over and over again every freaking day.
It's a nice sign out.
Proves it to you.
Larry.
Remember,
it's good.
You didn't prove it to anyone in this room, only yourself.
No, it's scripted, that, obviously. Or was that off the top of your head, Larry?
You have a good one, mate.
Thank you.
Cheers,
Nice.
Larry.
Surveying.
Bro,
He's
observations a bit closer than what you normally
I didn't expect that at the very end. Satellites proving the Earth from a surveyor.
Looking up at the sun measured the radius, so I mean, anything goes. I'm guessing.
Bro, he said a week. A week to take a measurement.
To measure an angle. Yeah. Oh, it's an expensive job. Highly trained individuals.
God, bro, I can measure an angle in under 4 seconds. You put the protractor on it. Bang,
don't be poaching their jobs. It's undercutting them.
Well, you know what? Until you guys get out there on a mountaintop and deal with the environment.
You want me to measure an angle? Big
and
job, that.
And get your big-ass wild T3 and get up on top of a tower and deal with night. Yeah. You'll find that that's a major undertaking, which if you're measuring across those kinds of lengths, yeah, you are measuring across the continent of the United States 20 miles, 5 miles, 80 miles at a time to get all the way across from Canada to Mexico.
You're just triangulating, right, Larry? Just triangulating.
Surely you can just come off the mean sea level one side and mean sea level the other and just meet in the middle.
Wait,
no, they're not doing elevation. They're just triangulating.
Oh, sorry.
Yeah, no elevations.
You agreed to that?
It did.
Triangulating.
As a separate procedure with separate instruments, they did measure elevations all the way across the country.
Yeah.
And and the triangulation is one aspect, and the elevation measures are a different aspect. So then you get your elevations and your latitude, longitude from sea to shining.
The elevation goes when they're measuring the horizontal distance from one point to the other, don't they? I mean, that's where they do the elevation, when they're doing that. And the triangulation's done with theodolites. Two totally different tools, like you say, for doing two totally completely different jobs. One measures angles, the other one measures elevations, and they chain it to measure the distance, the horizontal distance.
And with the vertical angles on the mountaintops, you can still get very good elevations, like they did in Mount Everest, with the vertical angles. No, it's not first order, but it's still very good.
So first order would be like a physical measurement.
Yeah, first order would be the guys with the chains and the auto level on the floor, wouldn't it, Larry? Millimeter accurate all the way across with that one.
Mm-hmm.
Yeah,
and nice and local too, so that you wouldn't have to worry about adding any other fucking measurements and like refraction and these other things they talk about.
Well, refraction is heavily studied and well incorporated.
Yeah,
you studied the bending of light. You studied random.
Yeah, that was George. George studied it.
Random atmospheric conditions. So random conditions that are different every day of the week, unique every day. We've studied them.
Let me
No,
get,
not
I'll
every
get a
day.
picture for you.
Every half an hour. What are you talking about?
Yeah, it's constantly changing, bro. You can barely get the same measurement visually twice.
So how
but
did you measure it?
In fact,
So how
at
did
the
you
minute,
measure it?
yeah, 2 seconds.
Come
then,
on.
they take the
Larry, I've
mean,
been-
they
Larry,
average it.
There
Sorry.
you go.
Yeah, Larry, sorry, mate. I've been doing some looking at the sea and the horizon. And I got a couple of cameras set up, not myself personally, but ones that are actually in situ, on companies' sides of their buildings and things like that. And I've just been like still shotting some of the images that I'm getting. Like when they pan round and they zoom out to this particular pier and then they scan round. And I've been like screenshotting and just seeing the difference in the actual horizon. This waterline is changing constantly. And so that's interesting. It's going to keep an eye on that and just.
And
I mean, if anyone's measuring to that, then that would be a bit of a problem, I think.
very good point. That's a very, very good point. Nobody uses the optical horizon of the ocean as a point of reference for anything. They always measure from the gravity vector, the plumb bob, vertical. That's because the horizon is useless unless you have a sextant and are on board ship. And then you look up in tables to get corrections for the dip to horizon, corrections for refraction to the horizon, because you have a sextant and that's all you have.
But what I will say though is, Larry, is that I've also got a sight level, and I said that I had looked through these instruments over long distances, never measured anything, just having a look. And when you pan the auto level round across the horizon, although the horizon of the sea is lower than the actual horizontal crosshair, it's the same distance off of that crosshair when I pan round. I think it was probably about, say, 200 degrees. And so there's no drop from left to right there. That's just a straight line horizon. But anyway, just thought I'd put that in there. Didn't know if you'd done that yourself.
Okay, that's a very good point you brought up. That when you put up your auto level and you're looking through the horizontal at your location, your crosshairs are looking into blue sky, not touching the water, not approaching the water. And as you go left to, and so as you at your extreme left, the horizon may be optically, the apparent horizon could be, say, 15 miles away. When you pan to the right, that horizon is still 15 miles away. When you look in the middle, that horizon is still 15 miles away. It makes an arc. And as you pointed out, that the crosshairs remain a constant height above that arc of the ocean horizon. Very good.
Let's just say that there's someone stood at that horizon that I'm looking at on the right-hand side, and there's someone stood on the left-hand side. Now, there's 15 miles between them, and you would say there was a drop from both ends, wouldn't you?
Well,
you say, like, the guy on there would be dropping from his point of view, and then the other guy, the other side, would be dropping from his point of view, though that when I see them both, neither are dropping. Now, that is a good point.
It's almost as if the drop is visual effect, not a physical drop. Wow.
Quite the opposite, because the crosshair of his instrument are looking at a blue sky.
But you're seeing, that's visual. You're not measuring an actual physical drop. Like if you had water and it was rolling off a curved surface onto the floor like a waterfall, but you looked at it and you're like, well, it looks flat, useless, because the measurement is actually it falling. So when you look, useless. When you measure the grade of water and see that it's not curving around a ball, empirical. So all you have is visual. That's why no matter where you look, there's drop. And it's always the same. It's always the same. There's not a flat spot on Earth. The Earth is a perfect sphere, yet it's not a perfect sphere. Yet everywhere you look, there's the same drop always, because it's a visual effect.
Wow, that's pretty good. I yield. I can only go with my own measurements. I can only go with the fact that my measurements agree with Ordinance Survey UK. And Bev says he's completely...
Slow. You didn't measure. You didn't measure. You looked through a scope. That's the visual. Okay. Now that would mean to go from one point physically to the other point and documentation, everything between them. When you just look, refraction, atmospheric conditions, all these things you make up don't give you a measurement, right? That's why if you had a ruler and you put the ruler to the other side of the table and you started looking at the rule and you couldn't really see it, the ruler doesn't care about the atmosphere. That's why the ruler will give you an accurate empirical measurement and your visuals won't.
Before this starts getting a little bit too heated, Larry, can I just ask you, you said you had 35 years of experience in surveying. What were you mainly doing? You know, over that 35 years, what was your main job?
Establishing control to make large area aerial maps, establishing control for large area civil infrastructure, geodetic surveying of many kinds, first order levels across large municipalities. Yeah.
Well, when you say establishing control, that's
to make the maps. Yeah, to make the maps.
Right, so you're going after benchmarks, right? You set the benchmarks in order for people, or do you transpose from the benchmark to find a new control datum, and that's your control that you're setting, the new spot, or what do you mean by establishing control?
As you know, maps are made from aerial photography, and in the aerial photography, they put fiducial points, which are these large physical white X's that we put on the ground that show up in the photography. And the latitude and longitude elevation of those white X's has to be established. That was my job.
The aerial photography, maps are made by measurement on the ground, right? And they're not made by aerial.
You see, and that you are so behind the curve, because aerial photography has been used for 100 years to make the topographic maps of every civilized country.
It's called photogrammetry.
Thank you.
Wouldn't those be 2D? Because they're from like right above.
Yeah, stereo photography, rectified against the fiducial points, and I put the fiducial points on the ground with its precise latitude and longitude of those marks show up in the photography.
Not for elevations, Larry. Come on.
Yes, for elevations, stereo photography, contours, photogrammetry. Yeah, you see, you really got to open up your mind and look at the industry. You look at the industry and what they've been able to accomplish. How did those maps of all of the UK get made? You know, yeah, they did it. They did it the hard way.
First order measurements, Larry. Actual measurements on the ground.
Yeah, well, and then they photographed the ground from aircraft. Yeah.
If you photograph the air,
you're
breaking up there. Yeah.
90.
Yeah. Hold on, it's a part of the house. If you're gonna photograph the ground from the sky to use for maps, it would only work angle-wise if the ground was horizontal. Because if it was curving away, the edges of your aerial photography is always going to be distorted, right? So the only reason that works and it all matches is because it's a grid, and it all is relative. It's all relative to it.
No, you have a very, very limited view of the technology involved, because the radial aspect of the lens is highly calibrated and using stereo photography and the fiducial points on the ground. No, you've got to open up your mind to the rest of the technology going on.
Technology is not going to. You can't see around a curve.
What
are you doing?
That's not first order measurements, is it, Larry? We're trying to get first order, right? Is that first order?
Absolutely not, man. You can't use electronics to get a measurement because you would have to verify the electronic put out is correct with a physical first order measurement.
Yeah, and that is done, and calibration is against. Yeah. I take my electronic. I take my electronic instruments to the calibrated baseline established by the Bureau of Standards to make sure that I'm getting the right answer and or minor adjustments and calibration. Yeah.
Where's your baseline though, Larry? What do you mean by you take your instruments to the baseline? What's that?
Yeah.
I just said so. I just described it. Our Bureau of Standards establishes marks that they have done their best effort to publish the distances and angles thereof, and I take my equipment to that array and I see if I replicate their published values. And they have put tens of thousands of dollars into establishing these array of marks, and then I get to use them. To
You mean the
confirm
benchmarks?
Okay, the word benchmark is a little sketchy here, but yeah, we're talking control marks that have precise values relative to each other, and I take my equipment and see if I can replicate my Bureau of Standards. Yeah, then I know my equipment is up to snuff.
Right, so you're not doing it to check your equipment, though, right?
Didn't I just describe I was exactly checking my equipment? Like you said, it's an elaborate version of peg test. Yeah, and then you make adjustments if necessary, or you get a calibration sticker that says I can do commercial work because this instrument meets specifications as established by the Bureau of Standards.
Yeah, but you didn't first establish these
Standards.
benchmarks with the scope. All the benchmarks or your points were established with a physical measurement. Then you just so you have, before you can use angles looking through the theodolite and yada yada, they all need to be first order measurements.
Yeah,
so
can
how
you see
is
that there,
done?
Larry? Can you see that in the live chat? That's a benchmark, right? That the ordinance have established, right? That's just a regular benchmark that they've established right now. So I know where that is. I can go and check up on the records, and there will be all of the exact positioning for that, elevation and everything, right? And then you can use that as an established benchmark that you can then work from. You just need to know the actual numbers associated with that particular benchmark. Now, that's not on top of a mountain or anything. That's just on the floor. And it's not just a nail that they've put in the UK. That's like an established benchmark into solid. Yeah, that's the one at the top of the top of things, right? For trig, yeah. So that's a triangulation.
Control. It says horizontal on it.
Yeah.
And it's a nice tower of Babel, by the way.
Horizontal
Right in the
control.
middle.
That's nice. Yeah, I like that, Larry.
Oh, wow.
Masonic eye in there.
Yeah, right in the middle. Nice.
Yeah.
1985. So right, so they're all points. Yeah, control points. Are they all horizontal control points? Or did you?
Some of them carry first order elevations, and some of them carry first order coordinates, latitude, longitude. And between the two, yeah, we have a network that is completely sound and accurate, and I can make my measurement, and they may be spaced miles apart, and I can establish points of fiducial for the photography by running between those points with my theodolites and my laser ranger. Yeah, I can do that. And I can carry elevation by vertical angles if that is accurate enough for the project, or I would have to run with my levels and rods if the project is to a higher specification. Yeah, it's a panoply of methods.
Oh, right. Okay, so what I was getting at is that they're already established, aren't they? All you have to do is just pick them up. Is that what you're talking about when you say they've established the baselines? Do you just go to one of those and then do some more sighting sort of points? Or do you then use that to make a new one of those?
Okay, an array of marks that are referred to as calibration by the Bureau of Standards is maybe a completely independent series of marks that are intervisible so you can check your equipment. These other marks were established by the agencies when they did the large area control works that span the country. Yeah.
And do those marks look like that?
They use a similar mechanical device of concrete poured in place with a bronze plaque and a catalog number and a lot of published values of it, and then I make measurements across those marks to make sure that my equipment is up to snuff.
Okay. Okay, so once you've checked your equipment, what do you do then? In order for you to control your whatever, when you were doing your job, what was it that you did?
I would set the fiducial marks that are going to show up in the photography on a spacing of say 5 or 10 miles, and then with my theodolite and my laser ranger, I would make a traverse all across those targets, beginning at one of those published marks and ending on one of those published marks. And then that all went away when they invented GPS. So I use satellite now, but back then, 30 years ago, I absolutely trucked across the ground with my laser ranger and my theodolite and measured angles the whole way, and then through all the careful computations done at the office level of the triangulation or the curvature of the earth and all that good shit to produce proper values for the fiducial marks that show up in the photography. And the photography was done with a $500,000 camera that has an extremely calibrated, carefully modeled radial distortion that has to be certified and also separately calibrated when dealing with federal projects, government agency mappings. Oh yeah. And they do a pretty fucking good job with known errors, known specifications for accuracy.
Larry, whoa. You're not even a very good storyteller. This is boring.
We have all the information, then we take it back to the office and we change it so it's right.
No, we take the measurements made
you did.
We take the measurements made in the field and
which are real, which are accurate. And now, why do you need to do anything to them? They're the measurements. They're done. You don't need to change them. You don't need to distort them. They're measured. They're empirical.
You got me. I just have an angle and a distance, and someone's going to want the coordinate at the end of that angle and a distance. I didn't calculate that in the field. I measured the angle and distance, and then the calculation was performed to get the coordinate at the end of that angle and distance.
Okay, but you're using this angle to get a distance that you already know.
Angle and, oh, fuck you. I told you I was establishing fiducial marks that did not already
established.
No.
With the thing in the ground, that's your mark. And before you did an angle, it was already put there. Because somebody physically measured it. What you're doing is checking to see if you can visually judge distance, right? So you already have the established marks. When you use a theodolite, you're going, is this thing accurate at this range? And your marks will tell you. And at a certain range, 50 meters, it's not anymore. That's the point of the marks.
No, you definitely missed the point of the conversation where I lay out the white marks that are the fiducials that show up in the photography, and those are not on those brass discs. I have to measure from those brass discs to those white marks, and those brass discs might be separated by 20 miles, and I have 5 or 8 or 10 of the white fiducial marks that are going to show up in the photography, and yes, I traverse between them with angles and distances, and then that table of measured data comes back into the office, and coordinates are generated for the white marks that were measured from the brass marks to other brass marks, so that the coordinate system is completely.
What are the white marks, Larry?
Yeah, you have the brass marks. Why are you putting extra marks?
Where's the white marks come from?
Because in the photography they need more, and they need them in specific locations.
What, like on the floor or something? Do you have to put them in between?
Wow. You know what? I gave it a shot, guys.
I'm just saying photography, right? So we know where the brass marks are. Are you saying where the brass marks are, you have to put a white mark that's a bit bigger so they can see it from above? Or do you put the white mark somewhere else?
I do both. I'll mark up, I'll lay a white target on the brass mark, and they need marks, say, every 1 mile or every 3 miles. And there are no brass marks exactly where they need them. So I establish these white targets. We've all seen them quite often. X's on the ground, They show up in the photography, and yes, they need coordinates on all of those marks, and there isn't a brass mark every couple of miles across the country. They were widely dispersed, and we're mapping an area like a county. There may be a few, 8 or 10 or more or less, I don't know, of these brass marks, but they'll need 100 targets. So we'll lay out the 100 targets. We'll establish the coordinates on those 100 targets from the 10 or 12 brass fiducials previously established by government agencies under great expense.
Nice. So that was your main job. What you were doing mainly. What was the?
I did that for a very long time.
Yeah. What was the best part of it? Like, what was the? Like, you must have a best moment of your career. You're not still doing it, are you? Are you
no,
retired?
I'm not still doing it.
Yeah,
but
you're
I
retired.
did.
Yeah.
I did find it very entertaining when I did that in Bosnia during the war. I found it very interesting when I went to the island of St. Lucia back in the early '80s. I did find it very interesting when I went to China to train people there as we were selling them equipment. I found it very interesting when I advanced into a jet airplane in radar mapping and mapped the Andes of Colombia. I found it very interesting when I went to Ireland, and I spent a lot of time in Coleraine and Belfast. And what's the one on the very southern part of the?
I find it interesting. You make a whole bunch of coordinate points on a 2D plane, right? So you have this flat piece of paper, and you mark all your brass and white marks, and then bam.
Yeah, that's it. Yeah, bam, bam, and then you go. But you got to go through all the math, much like the ordinary.
No, you don't. No, you don't. Why would you do that? You already have everything. You have the pictures from area. You have hold on. You have the pictures from the air, from the sky, which are 2D, right? A horizontal, and you have horizontal distances between all of those marks, which will perfectly match up in ratio to the real world. Yeah, you don't need to do any calculations. You have it all.
You know what? You need to go into the industry because you've obviously just trimmed out all the fat that we've been like running around wasting time and money on. You got to figure it out. Why aren't you like in business then? Because you would
know what calculations you're doing? You're converting the inches on the flat piece of paper to actual distances in the real world. But still, you're using horizontal distances. At no point, right? At no point during any of the calculations are you using geodesics. You're using straight horizontal lines taken from a 2D picture from above, and it all matches up perfectly to the Earth because the Earth is a horizontal plane. Congratulations, Larry. You did great work out there. I'm very proud of you. You served your country well.
And I'm very proud of your representation of the industry. That's great. Fortunately, the industry is much smarter than everything you just said.
The industry is working perfectly using grids on a 2D map taken from aerial photography. It works exactly like it should. And logically and mathematically, it works out that means the Earth is a horizontal plane when viewed from above, not a curved.
I'm sorry.
With satellites orbiting overhead. I love it.
Whatever, yeah.
Larry, 2 seconds. Larry, 2 seconds. I have a question regarding photography. So when they take an aerial photo in which there is an X on the ground that you put there, where should the X be on that frame of photo?
Well, it's laid out for the grid of where the photography will be taken, which is all stereo photography, all highly overlapping, and they'll need.
Again, I'm asking a simple question. Where should the X be on the photo that is taken from the wherever they take it from?
Hopefully, somewhere around 1/3 from the edge to the center. But there is a random aspect to where the.
Now, how do you do that?
By taking some previously existing map or some approximate layout of grid in our heads and say,
how do you count when you are traveling in any kind of airplane that goes like I don't know how many kilometers per hour, right?
The white
so
axis,
that little dot on the surface of what you are making a picture of will be at the very center, because if it's not, then
Yeah,
it's distorted, isn't it?
The white X's laid on the ground that are fiducial marks that show up in the photography do not always fall exactly where somebody would want them in the most optimal position. We lay out an array that is redundant enough.
Then if the Earth is a globe, then that picture worth nothing.
Well,
especially for calculations.
When it comes to the globe, the Earth being a globe, it's not an if.
That's not what I was talking about. I'm not sure if you get what I mean, but
The stereo photography taken from aircraft, and there are fiducials on the ground of sufficient density for the photogrammetric solution to be of integrity to satisfy the specification of the project.
what are you reading right now? Could you send me a copy of it?
I am not reading anything. I'm describing my job.
You literally read something. That was fucking obvious, but okay.
No, I don't have text in front of me. No, I.
Again, just for everybody else. So if a camera does not have a rectilinear lens, which it doesn't because it doesn't exist in real life, not the one that you would need in for mathematics. If it doesn't have it, then if your point is not at the very center, then that point is already distorted where it should be regarding, calculations of what you're trying to find out from a picture that was taken from an aircraft.
Which is why the photography is not singular pictures, but every point on the ground appears in no less than 3 individual photographs. And
For a theodolite, you need the object at the very center. But for the photography regarding aerial photogrammetry, you don't.
Well, in photogrammetry, using stereo imagery, every point on the ground appears in no less than 3 photographs at different locations throughout the image, and the camera has a very expensively calibrated distortion value applied to every micron of the photograph.
Every micron of the photo. What?
That sounds like it's being manipulated. to me.
The cameras, much like any other instrument, are calibrated. And a camera in the airplanes I worked in...
No, sorry. The image will be edited afterwards, by the way. I'm not sure if you know what you're talking about right now.
Yeah, you're right. Okay.
The camera cannot be calibrated for distortions. It always has a lens.
Are you
serious? You cannot. How do you calibrate the camera for distortions?
By taking it to a laboratory environment and photographing a very high resolution, very high precision grid. And the camera, which costs upwards of $500,000. In most of the airplanes I worked in, the camera costs more than the airplane. Yeah, that's exactly what you do. You photograph in laboratory environment, a very high precision grid. Yeah.
That sounds to me when I take my P1000
That's called post-editing. Post meaning after the fact.
No, the calibration
after
is done.
Took a picture.
The calibration is done periodically, like every 6 months.
Mate, I'm not sure if you certainly do not know what you're talking about right now. That calibration is regarding the already existing picture. It's not in the camera. I mean, there could be a camera which does it internally. Like there are cameras in which you can select what kind of scenery you want. You want the sepia filter or anything like that. But that's always done after you take an image, after you take the photo. It's called, again, post-editing.
I don't think he
And
understands.
it's only an approximation, by the way.
I think he's
It's only an approximation based on calculations. And you are right, by the way. You are right about the grid. You are right that that is the best way to calculate for the distortion that specific camera and lens introduces to a photo.
And there's the
You're
camera.
right about that part.
And there's a picture of the camera I'm talking about. That has the film stock on there is 9 inches wide and 500 feet long. Yeah.
But again, it's not physically done. It's not physically done. It's an algorithm.
Well, good. Then at the companies I worked for, obviously we were wasting our money doing stuff that you say is not done. So
No. That's not what I said. I just said that in photography, that's not how it works at all.
Okay, then
I don't know why you're talking about it if you know this little about that kind of thing.
Okay, you know, I yield. You're far more expert in it. You've been working in the industry much longer than I. So I give up. I yield.
No, that's not what I said at all. You are twisting what I'm saying.
Well, then maybe you don't understand. I've been working in the industry, and you have not been working in the industry. You're telling me how it works, and you're telling me the way that I have a poor to zero understanding of it. So there you go. I yield to your expertise.
I don't know. Anybody else heard anything like that from me? Because I literally was only talking about cameras and how do anybody account for distortion that is introduced by the camera lens. That's all I was talking about, not your job or anything like that.
Have you dealt with a camera that looks like the one I just posted?
Mate, that doesn't matter. Because
Okay,
every camera works on the same basis. No. Every camera works on the same basis. It's fucking easy.
Is this camera any different to the cameras that you know of? Is the question really?
No, there is a lens on the bottom. The same fucking way that any camera is, because that's what we call a camera.
Is Larry saying that the picture's being adjusted in real time, or after, or during? Sorry, I missed that bit.
No, he doesn't get it at all, I think. But he can describe it again if he wants to. Like, is the distortion, I mean, the accounting for the distortion happens physically, or how does it happen, Larry?
I'd like to know how high off the ground as well these planes go. He might be busy doing something. When he goes quiet, he normally puts more stuff up, like pictures in it.
Oh, he's
Did he leave?
gone. Yeah.
Ah, he did. I
Poor
was looking up
Larry.
this camera. I found it. It's called a Leica RC30.
Yeah. So what? It's $500,000 for that.
Maybe it's not listed. I don't think you can buy it as a consumer product.
No.
So I have no idea what it costs, but it certainly works on the same basis. Like,
Yeah, it's the size of it, isn't it?
that's
It's
what
like
we
he
call a
said, it was a
camera.
9-inch film. We say.
Yeah, it looks big, by the way. No problem there.
Yeah, it's just like, is your question then? You know, at what point?
Yeah. Would you look at the document I just put up?
U.S. Geological Survey, United States Department of the Interior. Okay.
Please keep reading.
Cool. Please
Lens
let
distortion.
it be
Okay.
the raising up of the St. Lawrence being higher.
The report of calibration of the aerial camera.
Kodak microflat. Yeah, I see that. Kodak microflat.
but you
Glass
just said-
plates.
You said lens calibration like can't happen. I don't understand.
What?
Well, this is done periodically.
When did I say that?
This is done periodically for cameras when you're dealing with large area, and yeah, that's how stereo photography can return against the fiducial place on the ground.
When did I say what you just claimed I said? Because I didn't. I said
Well, then I apologize for
it's not
totally
physically done.
I totally apologize for completely misunderstanding that your description of stereo image photogrammetry and large area topographic mapping was different than mine. I've worked in the industry, and you say you have not. So I don't understand why the "if the Earth is a globe" shit persists.
You are mixing up so much stuff in that one sentence, by the way. I won't even address whatever. I will just say that these are parameters. So parameters are used within calculations. They don't change anything regarding the camera. They change how you should perceive what is on an image based on these parameters. That's the same thing that I told you.
Right.
That,
Removing.
I only partially said that I know this because regular people do this, by the way, because consumer cameras are coming out every year. There's always a new lens, a new camera, and all of them distort the picture different ways. And people are doing this, by the way.
Right.
You can look it up.
And that calibration of the radial distortion of a specific lens is how the distorted image of an aerial photograph is related to its undistorted reality.
Yeah, but again, this kind of thing that you are showing in this document is for calculations, whatever you see on the image. Which means that the image is already done. It's already photographed. And then you can make calculations based on these parameters.
So when you see features on the ground, you get the camera coordinates, and it can be calculated into real-world coordinates so that there is no distortion of the map generated from the stereo pair photography and the calibration parameters, so that the XY latitude, longitude, and elevation of a point on the ground, as determined by a stereo image, that an element on the ground showing up in no less than 3 photographs, comes to a specific project specification of accuracy.
Yeah, basically, but the original question wasn't that. The original question was started out that if you guys, surveyors, when you do distances, for example, and you try to map out a map, like literally trying to draw out a map and write out the distances that you want on a map, do you use triangulations? Do you use simple triangles? Because if you do, then the triangles, are just straight line objects. They are not curved in any way.
Correct. If I'm observing from a ridge to a point some miles away, my line of sight is basically straight, and as that relates to the geodesic, that's a point of calibration or a point of calculation. And has been described many times. The Ordnance Survey being one of them, goes through the explicit math of how to take measurements across terrain, projected onto the geodesic of the shape of the Earth, and then further project that into a Mercator projection to generate the map. Yeah.
You got a problem with those projections. You know that, by the way, right? Like, for example, the ones that are showing, I think, Iceland being the same size as Africa.
Well, that's the Mercator projection, which is known to be,
Yeah.
yeah, and that's why you don't, yeah, if you're going to try to depict the entire globe in one page, yeah, there is a huge amount of compromise, which is why an area like the UK,
Compromise.
like the UK,
What I
has,
would like to know, because I get what you mean. That's why I'm cutting in. Sorry, I totally get what you mean right now. But it's not problems. It's not little problems. It's not like, we are almost right. Iceland is like 1/10 of the size of
and
Africa.
when viewing,
So when they come up with a map, when they come up at the very end with a map that shows me that Iceland is the same size as Africa, then I have a huge question. How? What did you calculate that made you, that resolution at the very end? Who calculated it and why at all?
when Iceland or Greenland, when Greenland is mapped,
Greenland, I think, yeah, sorry.
when Greenland is mapped specifically, yeah, then its area is accurate. But when projected or incorporated with large other areas, yeah, there are distortions, and you have to pick which projection you're going to use. Why? Because you're dealing with a very large area instead of just the area of Greenland. You can make a
But
separate
if
map.
your calculations are correct,
make a
and if
separate
your
map.
premise regarding it's a globe is correct, then why is it bad? Why the end result is so fucking bad?
If you make a map of Greenland specific to Greenland, as opposed to making a map that shows its relation to other continents, yeah, that's hard to do. And there are projections, and yeah, you can deal with the map. It's bidirectional, yeah.
It shouldn't be hard. If it's just a radius, it should work out.
Okay, and all that math has been laid out for us, yeah.
That's not what I said. I said there's a huge problem regarding the size of Greenland on a world map.
There is no problem with
compared to other.
There is no problem with size of Greenland.
On the world map, there is.
Yeah, when you're depicting a map that has the entire world on it, as opposed to a map that only has Greenland on it, and you can compare it to a map of South Africa that only has South Africa on it, and yeah, those areas are.
Is that the problem of trying to squeeze all these things onto some sort of spherical fucking concept? Is that where the problem is, do you think? Like in reality, it works out on our flat maps that are divided up into grids, like they are in England. You know, that's what we've got. We've got grid maps to scale.
Yeah, obviously, by the way, that's the problem. They are trying to use math for something that shouldn't be used at all. Because if you cannot develop a sphere's surface, then you cannot do the opposite.
Surely they've got pictures anyway, haven't they, of Iceland from fucking space, surely.
I'm not sure. I'm not sure if Larry knows that, by the way.
Sorry.
So if you cannot develop the surface of a sphere, then how can you do the opposite? Which we could describe as stretching a texture or a flat plane on the surface of a sphere. How can you do that if you cannot do the opposite? And you cannot do the opposite because it's written in mathematical proofs, right? Isn't that where the problem arises when they are trying to stretch the already established maps onto a globe.
think so.
That's my question to Larry. I don't know if he has like an opinion at least about it. I will wait for it.
Mhm.
He hasn't answered, by the way, why there is a huge fucking problem with the continents ratios on a
Yeah,
world map.
totally. Yeah, it's Europe, excluding Russia, is only a bit larger than South America, and Antarctica
But
dwarfs
that's just an
all
example. Yeah.
continents. Yeah, Antarctica dwarfs all continents. Yeah, that's just down the bottom of the ball, isn't it?
What do you even mean by same scale when you write that?
He's doing it from the same height elevation. 4165.
So that's Greenland, right?
Or something. Maybe.
So Greenland is the same size as Africa. Okay. Almost the same size. Sorry, it's not exactly, but almost. Yeah. That's amazing, by the way.
Wow. You're talking about 2D surfaces.
Yeah, that's what I asked Larry, and he won't answer anymore. That it's written in mathematics that you cannot develop the surface of a sphere. Therefore, you cannot do the opposite, can you? And he won't answer to that kind of thinking. I mean, that kind of thinking is called logic, but fuck the guy who came up with that.
I've just had my tea, so.
It's actually in already. Okay.
Cheers, mate.
Right, so while we were having tea, I was telling my lad about triangles with more than 180 degrees, and he's curious.
I think if you would say it like in a cafe shop, like we would go around and tell it to people, everybody would be interested in that.
I mean, I know it's advanced and he's only at school, like, but it's always worth hearing somebody say it. But you say he's gone, has he? He's gone quiet.
Now, if you would go to a construction site and talk to the guys that are working there, I'm not sure if they wouldn't beat you up right on the spot when you say that, but
yeah,
that's a different question.
I can't understand how a 3, 4, 5 triangle would work if you just made it bigger. It's like proportional, right? The 3, the 4, and the 5 could be anything.
Yep.
300, 3.
Yeah, I do it all the time, Bev.
Yeah.
I go like 4, 6, 8, or whatever, like. Or
Sure.
4, 6, 10. Sorry. Get that right. Shit. I'll embarrass myself in all.
Yeah, but it doesn't really matter like 4 meters or 40 meters, right?
No, that's right. Yeah.
The size of it doesn't make any. It's all proportional, right?
It's still straight line sight anyway, isn't it? Just
you wouldn't gain any angles anywhere.
No.
Otherwise, it wouldn't be a right angle, triangle. Like I really don't understand how it. Especially when you keep going to that map as well, that Are the distances the same across that? You know, just the grid looks different.
I'm on there now, having a little look, and I got some interesting.
Again, I still don't get it. How do you stretch a texture that we call right now? This texture we call right now the map of the Earth. How do you stretch it onto a sphere mathematically when mathematics tell you almost as an axiom that it cannot be done?
It is Gaussian curvature. That is a non-developable surface. You cannot express it in a two-dimensional plane. Cannot be done.
Yeah, and
it's
therefore
impossible.
the opposite is true also.
Yeah.
The opposite being stretching a texture, stretching a plane onto a sphere. That's the opposite of developing a plane from a sphere surface. If that cannot be done, then the opposite cannot be done.
Yeah, like not just mathematically, right? The true meaning of maths, the logic, it just doesn't even logically fit. There is no possible way for it to occur. Therefore,
yeah, that's what I'm asking Larry, and he won't answer that. I don't know why.
The 2D, 3D argument from geometry again. It's at the heart of this triangle thing. And the plane that we were setting out before, the three coplanar points. Larry got upset about me using that right at the beginning. That might be where it is, the problem.
There's more to it these days than it used to be, now that they think they live on a globe. It changed everything.
Alright, we're back.
Yeah.
Yeah. Right.
Do you know what I mean? The first order measurements are still there today. The same ones that he's got all his elevations from. You know, like, you know, he said that maybe some of the mountains haven't been. Those have to be worked out with trig.
Well, they have in the UK because that's what they use for the triangulation points. All of the peaks of.
Yeah, that's the bit I think it's quite an important question to ask someone like Larry. Is how can you put all that history aside and just go with what's now? And he's used those techniques himself by the sounds of it, or the older techniques. What changed?
I don't know. In the 35 years that he's been doing it, supposedly, it must have all changed, right?
Well, yeah. I mean, the tools they use, but I mean, why would that ever change reality?
Yeah, well, even I've got a land surveying certificate, so I mean, it wasn't geodesy back then; it was land surveying.
Yeah, Larry, do you see the ones that I posted right there?
He's gone into what they call over at Jose's, all of the trolls, a meme spam. Just spamming things, but I mean, it's not spamming. You know, you found something that you think supports your case, and you just putting the pictures up there, right? You've got 35 years though, supposedly, Larry. 35 years of practical experience. Why do you have to go to Ordinance Survey, the UK? It's really strange. Really, really strange.
It's because they've written it down for him.
I brought up the Ordnance Survey UK because you say you perfectly agree with them. So when the Ordnance Survey brings up the Gerasati ellipsoid, Mercator projections, the method of getting projections onto their maps, which are projections, yeah, that was common ground.
Larry, did you see what I posted to you? It's from nationalgeographic.com, but you will find this kind of claim anywhere you look around regarding the Mercator projection. that the popular Mercator projection distorts the relative size of land masses. Now, how is that good? That's my question. That was my first question to you. If it distorts, then how is it accurate? That's
Well,
basically those words are basically opposite of each other.
That is why areas are mapped in zones. So the zone that UK is mapped in is specific to UK and not the same definition of mapping zone for Greenland or the state of New York. Yeah, to reduce those distortions, because everything is a compromise when you make the projection. Distances will have scale factors of maybe a part in 20,000. Areas will have scale factors. Orientations will have scale factors. And they're kept to a minimum by segregating into the numerous, the many, many different mapping zones of any one particular map. So if you're only going to display an area the size of Scotland, you will have a slightly different projection, which will have slightly different compromises than when trying to display something as large as France, Germany, or Greenland.
Can I ask what a scale factor is, Larry, for distance?
The scale factor is the difference between what you measure on the ground and what you would measure in the map.
The map is a two-dimensional representation, a horizontal distance, right? That's what you measure.
No, and it's not. The map is in grid. The distances you get on the map are grid distances.
Yeah, horizontal distances, Larry. They are the UK. Yes, yes.
No, they are specifically identified as Mercator grid.
It's straight line distances, Larry.
Specifically,
but again, everybody tells you that the Mercator is not right. Why are you jumping over the fact?
It has compromises, and if you do very large areas, you get very large compromises.
Larry, these are two-scale maps, 1 to 50,000.
Areas, smaller segregated areas, like just UK, then you have a much smaller magnitude of those compromises.
The whole of the UK, Larry, all on one grid system.
Yeah,
all
isn't
1
that
to
amazing?
50,000. Well, you can go even closer than that, right?
Yeah. You know, just one of it.
All on the same datum, the old same sea level.
Dive into their publications, and they'll explain it to you.
The two-dimensional maps that they have, to scale.
Yeah, and if you read the Ordinance Survey's documentation, they'll describe it to you.
What will they describe about a two-dimensional map system where the triangulation and the horizontal distances are all accurate and to scale? What will they explain to us?
Scale, as you just said, to scale. And if you dive into their documentation, which I am not going to summarize because I will miss things, I will misspeak, read their source documents on how to equate a distance you measure on the ground to the distance you get on a map.
It's the same, isn't it?
So it's not the same, that's what you're telling me.
Yeah.
Right now, or else, sorry.
Right. Dive into their source documents. They'll tell you.
So the triangulation on the map doesn't work in reality.
The distance I would get from a map will not match what I would get in real life.
Correct. And they tell you how to equate them.
Sorry. Then what the fuck is a map for at all?
It tells you on the bottom. It tells you specifically what the magnitude.
He's not talking about the Ordnance Survey maps here in the UK because they're all to scale. Like, I don't know. He might be talking about American maps, but he's not talking about the UK maps.
Okay, they're all to scale, and they describe the scale and how to equate the reality of your measurement to what they ended up having to do to get onto paper. Yeah, and it's bidirectional. Use the scale factors for what you measure on the ground to what you get on the map, and how to go back and forth between latitude and longitudes and Mercator grids, all in a very, very elaborate bunch of math to make a map which is described as compromised because the compromises are kept to a minimum by dealing with smaller areas.
To scale, Larry.
Or, as far as I know, scaling basically and very simply means that there is a scale on the usually on the right bottom part of the map. Now, that ratio, which says, let's say, 1 to 50,000, it means that if I would take out my little ruler and I would measure a distance in between some points on that map that I have in front of me in a book or in just a plain printed out version, if I would measure with a ruler, then all I have to do is multiply what I get by 50,000, and that would be an accurate distance.
Correct. And your ability
Exactly.
to measure on a map some tens of centimeters, you can only measure to...
Then where does any radius come into the calculation, if that's true?
Hold on. If you measure across the map some tens of centimeters, you can only measure, give or take, a fraction of a millimeter. And if you take that scaled distance on the map and multiply it by 50,000, yeah, give or take a tenth of a millimeter times 50,000, yeah, you're going to find that is
But that's not because of the radius. That's because my ruler is not precise enough.
Well, neither is a paper map. Paper expands and contracts with humidity. Paper maps have compromises in the printing process. Yeah, if you're looking for a part in 100,000 or a part in 200,000 precision, you're not going to scale it from a map. You can't scale a map to a part in 10 parts per million, and the map was not generated to 10 parts per million. It was generated to a part in 50,000, which is 200 parts per million.
The map was measured in 1-to-1, Larry. Measured,
by the way, yes,
actually
it was
measured, and then it was scaled to the map, Larry.
And it's not scaled by hand, by the way, especially nowadays. It's scaled by a computer that uses simple math for that, and it uses 2 coordinate calculations for that, not 3. Scaling doesn't mean that.
You know what I suggest? I suggest you get some survey equipment and measure between the brass marks, and then calculate the distance by the haversign, and you'll see the difference.
If you measure the distance, what's the point in calculating it, Larry?
Because you'll see the difference to what you measure on the surface of the ground and what you calculate to be the geodesic. You'll see that difference.
But then we are just calculating something that we have in our mind. We are talking about measuring. We already have the measurement.
How
Why
do you
would you need
calculate a
more
straight line
numbers after
distance
it?
that you've already just measured? What are you doing that for, Larry? Again,
take the deep dive into Ordinance Survey documentation or the U.S. Survey Office's documentation. They'll describe it to you. Go to Oxford. Look at their geodetic department. Yeah. Deal with the Earth on planetary scales or on county-wide scales. Yeah, they're very different magnitudes of dealing with the compromises when generating a map.
there's no difference in the size of a triangle, Larry. It doesn't affect them. Like, straight lines don't bend when they get a certain distance.
Okay.
Triangles don't gain extra angles for getting bigger. It's ridiculous, Larry.
Well,
I'm really considering questioning whether you are actually a surveyor.
Okay. Good. If you don't get your equipment and go out there and measure it and test it yourself at big distances, then I yield.
Well, you have to measure a big triangle first before you think.
It's going to be hard and expensive, and that was done and documented.
It wouldn't be expensive. It would take some time, but it wouldn't be expensive. What are you talking about?
Okay, all you got to do is get your your $15,000 piece of equipment, get your multi-man crew, and get out there.
Why are you talking about money so much, by the way? Like, Bev, what is the price, the approximate price that you bought your auto level for?
100 quid, 99 quid. UK.
100 quid?
Yeah.
Hmm. And do surveyors, my next question, do surveyors use that daily?
Well, yeah.
The same
For
equipment?
elevations, yeah. That's the first
Then I
order.
don't
Even
get how-
Larry said
how
that's how you
does-
get first order elevation
Yeah.
measurements. With that tool.
Then I don't get why Larry is talking about $50,000 at all.
The level
Is it-
surface drops down from the horizontal plane at a rate of 8 inches times the distance in miles squared.
I'm not kidding.
Are we gonna keep on dividing? Are we gonna keep on fighting? Are we gonna keep on dividing? Well, are we gonna keep on fighting? Are we gonna keep on dividing? Are we gonna keep on fighting? Are we gonna keep on dividing? Well,
level.
Straight lines don't bend when they get a certain distance.
Okay.
Triangles don't gain extra angles for getting bigger. It's ridiculous, Larry.
Well,
I'm
if
really
you-
considering questioning whether you are actually a surveyor.
Okay. Good.
My lad wants to ask you a question, Larry. And
Yeah.
see if you can do your best to help
Muted
him
right
out.
now.
Well, it's all right. He's listening.
Yeah, Larry. I want to know a bit more about this. How these triangle angle expansion or something works, because I've heard it from a dad and it sounds a bit ridiculous, but I want to hear it from you. So if I can understand it a bit more, you know.
Your volume's so low I can't hear you.
Sorry. Yeah. Can I hear a bit more about this, like, triangle angle expansion or something you were talking about? Possibly.
Sorry, do you mean triangles having more than 180 degrees?
Yeah,
as
that.
a sum?
Yeah, how it,
Okay.
like, when it's small, yeah, it's 180 degrees, but when it goes to a larger scale, it somehow gets more. I want to know a bit more about that, see if I can understand it.
I just posted what the math is involved when dealing with planetary, county-wide, statewide, large area. That's the math you go through to deal with the triangles, because the instruments are oriented to vertical at each vertices, and plumb lines are not parallel, as we know.
Well, I'm not going with what you've given them. I'm trying to just understand the whole concept, because I'm, like, as you said, I'm a bit young. Just want to know how it works, because from school I've heard triangles only have 180 degrees and all this stuff, so I just want to know how it can have more than that. Like, how? Not just the math involved, but an explanation.
Well, I just put the math up there, and when you get out in very large distances, it matters. When you're measuring over very small areas, it's hard. The difference is very, very small. So, yeah.
Yeah,
Given the
but
shape,
how
given the
does
size,
it have more than 180 degrees?
I put the math on there because
It's not just... I'm not talking about math. I'm trying to get an explanation from you, not just some paper.
Because in a large area with many tens of miles per side and hundreds of square miles encompassed by that triangle, each instrument is oriented to the vertical. And the vertical is not parallel at two points separated by any real distance.
Is he still going fucking on?
My lad's trying to work out.
Yeah, I'm hearing him talking about this, but he's talking about, like, real life but like triangles shouldn't be. It should be impossible for a triangle to gain more than 180 degrees because it is a triangle. It has three angles. When they're lined up together, the mathematics involved can only have 180 degrees. It cannot go more nor less, how big or how small it is. And that's what I understand and I've given as fact, and I'm still thinking about it, and it still seems true. I don't know how in real life it's wrong.
Yeah, it doesn't really need any more consideration, really, does it, Larry? Because he's struggling now. Can you hear him? He's like wondering on the concept of a triangle having more than 180 degrees. I mean, it does sound fantastic. Can you give him some help, Larry, please?
Because the spherical excess increases at about 1 arcsecond per 75 square miles. So if you're measuring a triangle that has 250 square miles, you only have a couple of arcseconds total accumulation, and that is distributed across all three vertices. And yeah, that's only like not even an arcsecond per angle, and that is small, and that is a singular arcsecond to high reliability is a serious measurement undertaking.
So, at what point, Larry, does a triangle, when you start with a normal triangle table, how much do you have to increase that for it to start gaining, like, the size and the angle start gaining? How big does it get until that point where it starts gaining on its angle?
Well, at 75 square miles, you have 1/3 of an arcsecond per angle. So if your triangle is only many hundred acres, yeah, the spherical excess is minuscule. But when you get into measuring a triangle that has 800 or 900 square miles, you have a few arcseconds.
So what you're saying is, if you were to have a normal triangle on a table and then just a tiny bit bigger than that, it's always gaining in angles. It's just until that point you're able to see it then and only then, because it's so small of a difference. Is that what you're saying? Trying to understand a part of what you've been saying with this whole conversation, not just the whole, because the whole doesn't make absolutely any sense.
You can't measure a triangle on your table that incorporates hundreds of square miles.
Well, does it, like, if you had, like, let's say, some brilliant tool that you would be able to measure some, like, the extremest of smallest of differences, would a small triangle on your table compared to a triangle just a tiny bit bigger than that, would you see a difference in them too?
No, because you'll be measuring the triangles on your table with a protractor at each vertices. That's all in the plane of the table. But when you get out in the real world, when you level up your instrument to the local vertical and you go 20 miles away or 50 miles away and level up your instrument to the local vertical lines are radial to the center of the earth.
So even if you had the best instrument that you'd be able to calculate like any distance between the smallest of points, you wouldn't measure. If you were to have that instrument, not just a normal protractor and all of that, would you be able to see a difference? Yes or no? That is the question.
In theory, yes.
Okay.
In practice, no.
Okay then.
Because each of the instrument at each vertex, if it were oriented to vertical lines are not parallel. But if you're only dealing with something the size of the interior of a room, those numbers are too small to even contemplate. That's why it only shows up when dealing with triangles incorporating hundreds of square miles, and the instruments are oriented to the local vertical at each vertex.
Okay,
And
so
vertical lines are radial to the surface of the Earth.
you're talking about a 2D triangle, correct? Two-dimensional.
I'm talking about a triangle measured across our Earth, which is a planet. Yeah.
So two-dimensional. So where does vertical come in?
Because that's how your instrument is oriented.
Thought it was two-dimensional though. How can an instrument be oriented in any other way if it is not? If it is two-dimensional?
You know, it's a complicated subject. I gave it my shot. Take the deep dive, the Ordinance Survey, or any other large geodetic textbook will explain it to you.
All right then. Thanks, Larry. I'll try and keep a look into it.
Given the existence of the South Pole, sunrise, sunset, orbiting satellites, eclipses, and tides, yeah, flat is not an option.
Thanks for that, Larry. How do you think my lad did? I think he did very well. I don't think he got anything
Me
sorted.
too, by the way. Me too, by the way.
He will be looking into it. It's like when people hear these really strange things that they've never heard before, Larry, they get inquisitive. And they want to come and ask the people that say these things how they know that and why they say such things. I'm still of the opinion that triangles only have 180 degrees. I mean, I think you're mad. I think you're claiming that you can do impossible things.
Well, so does the Ordnance Survey. So I could agree with them or I could agree with you.
Well, the Ordnance Survey think you're mad as well. Is that what you said?
The Ordnance Survey has vast wealth of published values on dealing with the large area triangulations. So
it's well known in mathematics, though, Larry, that triangles only have 180 degrees.
Yeah, except when dealing with a sphere, like the shape of the Earth.
A sphere is a surface of constant curvature. There is no straight lines on a sphere.
Well, you have the line of... If you
Can I phrase it?
2 points that are in a line of sight, yep, that is a straight line. How that equates to the shape of the Earth, yeah, that is a point of math. And I could agree with you, or I could agree with Ordnance Survey UK. I'm going to go with Ordnance Survey UK because that matches my experience. What you're saying does not match my experience. I can't go with anything Flat Earth says.
Larry, I'm just saying triangles have 180 degrees. I can't let that go. What's up? Sorry. I'm saying triangles have 180 degrees. That's not flat Earth.
Okay.
It's mathematics.
Take a soccer ball and draw a triangle on it and measure up those angles.
You can't measure an angle to a curve, Larry.
Oh, okay, yeah, there you go. Then we're done. I don't know what else to say. You said you agree with Ordnance Survey UK, and I thought that was common ground. I bring that to the fore, and they're all about the shape of the Earth, that you do not agree with the Ordnance Survey UK, apparently. So I brought that up as common ground.
They don't measure angles to curves, the Ordnance Survey.
Except when they say they do.
Wow.
If you enjoyed the content, please support On the Level and future projects. Membership subscriptions available now, or come and get involved at Next Level Discord server. Thank you.
Given 3 sides, A, B, and C. Right, so you've already been given the sides of the triangle in Larry's one that he gave to my lad. I wonder if that's in data. Spot on. Yeah, have a look, see if it's got anything to do with spherical triangles in data.
Hello?
Yo.
Sorry. You asked me a question then?
Yeah. I wonder if there's... Have you had a look into any of your books yet?
Well, a little bit of a dive.
Have a look. It'll be at the end of of data. You know, things that can be worked out from known things. Have a look, see if there is anything to do with spherical triangles. Because what Larry's just posted might actually be in there. If it is in data, then it's spherical trigonometry that they're just repurposed as spherical geometry.
It's right beside me. I'll have a look. I've just got to make sure I've got no salt and vinegar on my fingers when I...
Yeah, you don't want to be leaving marks on that.
Yeah.
Get your gloves on.
Yeah.
Did you say that was your son speaking with him? I missed quite a bit today.
Yeah.
Near the end.
Yeah.
That was Yoda?
No.
That was your young one?
Yeah.
No way.
Yeah.
Wow.
Got
Shout out to you, my
Getting
friend.
a bit of a team here together, right?
Wow. That was awesome, man. Yeah.
Yeah, 15-year-old autistic lad.
Wow.
They're in
He's
trouble,
one
aren't
smart
they?
kid. Oh, shit, yeah. Wow. That's one of the best things I've ever heard. Shout out to your lad. I was wondering who that was. I didn't want to interrupt, you know?
Yeah, feeling quite proud right now.
You should feel proud, son. You should feel proud.
Is he coming back? I think Jose might be going live. Oh, Brad's in. All right, Brad. It's all right. We won't want to press you. Okay. Nice drawing, though. I see you've moved up into graphics. Got away from your ballpoint pens. That was pretty impressive. He's just gone extra rumpus. You like a low grade rumpus.
You like my paint?
Is that what it was? Paint?
Paint, yeah.
Yeah, cool. Definitely a step up.
Yeah, that's...
Has Rumpus been teaching you that?
He's my mentor.
Yeah. Did you hear much of Larry?
No, just a little bit. I'm at work. I couldn't really hear it. I cut a couple minutes. Is he schooling you guys?
Well, I don't know. Have you heard about triangles gaining more angles when they get bigger?
Define schooling. Yeah, it's spherical X.
Right, okay, so what size is the triangle that has 180 degrees?
What size?
Yeah.
I don't know how to answer that.
Well, you say they get more angles as they get bigger, right?
On a curved surface, they have more than 180 degrees.
Oh. But no, Larry was saying it's like the triangle is 3 coplanar points. And as we were doing from mountaintop to mountaintop to mountaintop, right, 3 angles, getting more. As the triangles got bigger, the angles gain more to each angle, right? Not just one side gain an extra angle. Like all of them individually gain a proportion of the angles that they gain more than 180.
Oh, I see what you're talking about, yeah. But on a surface of a sphere, I don't think it ever can have 180.
No, Larry was saying that when normal triangles get bigger, they gain angles. Pretty sure that's what he was saying.
I'm not sure about that.
We were talking about triangles, 3 coplanar points. He knew what a triangle is. I mean, you know what a triangle is, right?
Was he talking about a spherical triangle? Is it a spherical triangle? Yeah.
I don't know. You can't measure an angle to a curve, so.
Yeah, that gets kind of tricky.
Yeah.
Impossible.
Yeah, more like impossible.
Impossible.
Mm-hmm.
Impossible. Get it?
Impossible ball. Where'd Larry go?
I haven't seen you for ages.
Yeah, Larry just left for a bit. I don't know. He's been in and out, popping in and out all day.
Oh.
Yeah, there's quite a bit in this data. There's lots to.
Is there anything to do with the spherical? Right, it should pop out really easy.
Well, it's just before the spherical trigonometry, isn't it?
The data is, yeah.
Is start of. There's nothing really. I've been through it once, but I'm looking for.
Well, can you see that spherical triangles given 3 sides A, B, C? I wonder if that's in it as well. He's got to have got that from somewhere. And it wouldn't surprise me if it is in data.
What bit are you actually looking at? Something that Larry put up?
Yeah. Page 349. Entitled Spherical Triangles.
Where's he put that? I can't. Oh, sorry. Yeah. It's underneath the.
Underneath is the
The
other
tripod and whatnot. Oh, okay, yeah. 349. That's interesting because hold on, I'm on 3. Yeah, 49. Yeah, I've got that page. So it's to a circle. Okay, and so it might be related to that then.
What do you reckon to that, Brad? What if Spot On's got it in his book and it's spherical trigonometry, not spherical geometry?
I'm probably better off taking a picture of this because I'm not the best reader, so and there's a fair bit there. But it just seems that I'm on. It's mentioning circle here.
Yeah, I've heard that spherical trigonometry.
Yeah, it's not spherical geometry, is it?
Not sure about that.
Oh.
Spherical geometry.
Learned Mr. Moore, Professor of Greek in the University of Glasgow, observed to me that it plainly appears from Archimedes. I can't even pronounce that. Prefixed to his books of the sphere and cylinder, which epistle, that's the word I can't locate, because you got in this, the F's are S's, aren't they? It's a bit tricky, but he was restored from ancient manuscripts. Eudoxus was the author of the chief propositions in the 12th book. Then it goes on to, at the beginning of this, it is said, it is to be not foe, the square of B, D shall... That's what I mean, I'll take a picture of it.
Yeah.
But I think it may have a relationship to it, I'm just... Like I said, not the best reader. I'll just take a picture of that.
Yeah, the angles. You see the angles in there, Brad? Where it says the angle. Can you see that, Brad?
Well, it hasn't got any of this workings out on mine. It's just it's written. It's certainly not the same as that, but
on your thing, Brad. I think you're being tricked. Personally. Copy. You've got the angles are in between two planes. They're not in between two curves. Like we've been telling you all along. Sure, I took you in there to work that out. The angles are between the planes. Internally on those internal angles. What have you understood from that spherical geometry then, Brad? You've been posting the videos quite a lot.
Yeah, have you checked any of those out?
Yeah, what did you get out of them?
I don't know.
Have you not checked them out?
Yeah, I've seen quite a few of his videos.
Okay, so
he's pretty good.
What did you get out of it then?
I need to work harder on geometry.
Right, well, it's all,
That's what I got out of it.
It's okay, because when you learn that you surveying, in reality, they just use Euclidean geometry, you know.
I found a video on spherical geometry.
Yeah, there's loads of videos on spherical geometry, but in reality, when surveyors use this and they measure everything in reality, they only use Euclidean, right?
Not sure about that.
Even when you come to put it on a map and everything, all of that sort of stuff, that's Euclidean geometry. Horizontal, straight line distance, directly proportional, scale it, put it on a piece of paper. Call it a map. It's Euclidean. If you put in the Euclidean geometry and then go and find the uses of it, it will say the first thing is surveying. Because they use Euclidean Book 11, solid geometry principles. But what sort of surveying techniques did you see in your surveying things that you did? You know, when you were looking through your videos that you were watching, what did they say there? Spherical geometry in reality, or was he just holding a ball? Drawing shapes on balls. Have you ever watched that series of the Illinois Surveyor, Brad?
No, I haven't seen that one.
Wow. Okay.
Illinois Surveyor. I like the Maine Surveyor.
Oh no, this guy's a real surveyor.
Oh, real?
Yeah, he's much more informative. Much.
Well, he actually does surveying, doesn't he? He knows. He shows you
yeah.
how to set his tools
Proper.
up, not sets them up wrong and then shows you pictures of them.
The Illinois Surveyor, is that on YouTube?
Yeah.
I'll check it out.
Yeah. Wait, watch out though. Please don't comment and call him a flat earther in the comments, and please don't get triggered about it. With some of the stuff he says.
Remember, there's hills.
Yeah, he'll tell you how to survey it, how to do elevation, how to set
Don't
up the
forget.
tool.
Don't forget about the hills.
He does say horizontal a lot though, so be careful.
Did you see my diagram on the, what would it be called? Horizontal plane? Plane of the horizon.
Have you done it? I know. What? Let's have a look at it. Have you got it there, or?
Yeah, it'll take me a second.
I think it. Have you seen the logic thing? It's caused a bit of a stir, hasn't it? Over on Jose's. I don't think they know how to deal with it.
Well, they'll just repeat something that they think someone else would agree with them with, and then that'll do.
There you go. What do you think of that?
It's not horizontal, is it? It's
Yeah, it
definitely
would be.
on a massive tilt. What do you mean it would be?
Well, it doesn't matter on a globe. It doesn't have to be on the top. You could be on the side, the bottom. It doesn't matter where you're at. Horizontal could be anywhere.
No. For horizontal, yeah, it does matter. It has to be in the horizontal position.
I could spin that picture around so it would be on the top, if that helps. But what I'm getting at is the horizon is a circle of sight, right? So you have a circle. And the plane would. Your horizon.
Did you just make a premise at the beginning there that the horizon is what?
It's a circle.
No.
It's your circle of sight.
No. It's not.
Yeah.
Where's it mentioned as a circle?
It's my hypothesis.
Oh right. Yeah. Okay. You're assuming.
So, if you're on a globe,
Oh wow! There you go. Nice start. Right. Okay. I like it. Logic.
Imagine. Imagine.
No. You can't use logic and then plop imagine in.
Okay. If you're on a globe,
can we say if the Earth is a spherical object?
If the Earth is a spherical object, your horizon would be a circle.
Then
Your horizon is a circle.
Then a plane would go through that circle, or it would contain that circle. It would be a plane. That would be the plane of your horizon.
Right.
Do you like that?
Okay. But are you saying if the Earth is a spherical object, you realise what geometry you'd be using for that premise to be true, right?
Spherical geometry?
Okay, right. Now, spherical geometry is the geometry of the two-dimensional surface. Yeah?
Yeah, sounds good.
Okay, so how do you fit a plane on a two-dimensional surface?
Well, if you look at that picture, the plane goes through the sphere. It's not on it.
But that's not a two-dimensional surface. You can't go through it because the plane is a two-dimensional surface, but you're doing geometry on the two-dimensional surface of the sphere. You've got a bit of a conflict. You can't have a plane being a two-dimensional surface and the surface of the sphere being a two-dimensional surface. You've got a law of non-contradiction problem there. Massive one.
Well, the sphere itself is 3 dimensions.
Oh, okay. So you're using Euclidean geometry then? You're not using spherical geometry. You're using Euclidean, a 3-dimensional sphere.
How about just geometry? Can we call it just that?
Well,
what does Euclid say about that?
What does Euclid say about geometry?
What would he say about a plane cutting through a sphere.
I don't know. Can you find something to back your case for it?
I could look. You're the master of Euclid. You should know.
Well, that would be book 12, I suppose. Maybe book 12, maybe book 13. I don't know. Spherical trigonometry.
When I think of the plane of the horizon, that's what I'm envisioning, is a plane running through that circle of sight.
You're envisioning you stood on top of a ball, aren't you?
Yep.
And then you going along, I presume. Have you heard of the Black Swan?
Oh, yeah.
So do you agree with all of the numbers contained in the Black Swan argument for your circular value for where you position that geometric edge of your circle that you're making?
Well, I wouldn't use the Black Swan to get numbers off of because of all the refraction that's going on.
Or what refraction? For that won't affect geometry. Geometry's got nothing to do with refraction. You're talking about the geometrical shape and the geometric edge.
But if it's lifting things up or distorting things,
it's geometry. You really can't make, this is geometry, Brad.
I wouldn't put numbers on that picture. That's what I'm saying.
You wouldn't put numbers on it.
No, I'd go to a clear image where everything's not distorted. Then you could make some assumptions about it. But I wouldn't go to something that's that distorted and everything's crooked and wavy. And
okay. So that plane on there that you say is horizontal, is that what the water would be doing at that point?
Not sure what you mean there.
I mean, like water on the plane. If you were to have a water level.
The water level would curve around the surface of the Earth, the curved spot, not the flat plane.
Curve? Wow.
Yeah.
Is that a drop away from you or a slope away from you? Or is that a hump?
It'd be a drop away from you. The hump is only talking about a chord.
Okay. Like Blue said, a slope. The water always goes away from you. Oh, wait a minute. He said it always drops away from wherever you put your auto level up.
There you go. It drops from your horizontal.
Right.
The only time you would get a hump is if you're looking through the Earth and you're talking about a chord.
If you were looking through the Earth, can you can you do that?
Nope.
Oh. Can anybody do that?
Oh, maybe Superman. You ever watch Superman movies? Hey, I got to get back to work.
All right. Okay. Thanks.
Later.
Wow. It's a full jam-packed day today.
Wow. The delusion is thick today.
Well, some may not think it's a delusion.
Somehow the hump, they think it has relation to the chord somehow.
I can't get over triangles having more than 180 degrees. That's absolutely ridiculous.
Well, that's insane.
Grown men that pretend to be surveyors.
Yeah, I was explaining it to my wife, and she's going, "What? They're bending the lines? Then how is it a triangle?" I go, "Exactly."
They're going to come with It's been setting this up for years, right? The flat earthers are stupid. And it turns out flat earthers are just people that know and understand reality. Mathematics, general principles. The foundational principles of mathematics. Anybody that goes against that is going to be deemed to be a flat earther and stupid.
Yeah.
Yeah, I wouldn't advise it.
Well, I mean, the average person, right? if the average person were to engage with somebody like Larry, what would happen? I mean, obviously Larry would have more of his friends in tow.
Oh yeah.
And they'd just get annihilated for saying that triangles have 180 degrees.
Mm-hmm.
This is bad.
Especially when you got the Ordnance Survey backing you up.
Well, he hasn't got the Ordnance Survey backing him up. He just says he has. That's bad.
This is bad, but we've heard worse.
Yeah.
No one forgot the 5-sided square.
And the one-sided triangle.
In a book.
And the one-sided triangle. Yeah. If you enjoyed the content, please support On the Level and future projects. Membership subscriptions available now, or come and get involved at Next Level Discord server. Thank you.